So welcome back. Nice to see at least a core group of people repeatedly coming and staying for long periods of time. It's always good. So we're going to, this series will have, including today, three workshops. We'll do two more. And after that, we're going to switch to a slightly different mode. I'm going to repeat this during the break because I think more people will hopefully come. But if you are doing any projects, so there are two things. Somebody said they'll come and make this presentation on sentiment analysis. Here? Okay. I think he had done it in Chennai Pai group. So if any of you want to come and make a 10-minute, 15-minute presentation, let us know. We'll give you a slot. So in the we won't take away Ronajai's slot. He has to slog every week. But in the other, like the lightweight stack, we'll take a few presentations. We may actually do 4 or 5 of these 10-minute lightning talk kind of stuff. So that if you have built anything that you want to come and show, I know Karthik did some stuff, though I think it's not working now. Working, okay, all right. So there have been people who have been telling us that they want to come and present about sentiment analysis using Python, and so if you want to come and show something, you're welcome. You just let us know. Send me an email, and we'll slot you for at least maybe 3 presentations over the next couple of times. Okay, couple of workshops. I started a meetup group for value from data. I don't know what I called it, but I'll publish that in the Facebook group. The meetup is typically less intense than this workshop. We can meet for 1 or 2 hours in the evening of some day. We can all agree on the time, and so you don't have to wake up on Saturday morning and come here. And then we can talk more about the projects we are working on, the technologies we are using, and it's general discussion format kind of stuff. So we'll do that. Today we are going to do, there was also, I think Gaurav mentioned that we should do some Kaggle competitions. So these are the kinds of things where if you opt in, if you are interested in doing it, we'll form one team or group, and then we can do these kinds of things, right? These are beyond this mode of teaching and learning kind of stuff into self-learning and then practicing and doing all kinds of things. Don't worry only about Kaggle competitions. If you have a project that you want to build, you can post it in the Facebook group, or we don't have any other place to post, but I know that you don't go to Facebook. GitHub. You'll make it a comment in your this thing? Or? Oh yeah, okay. So we'll give access to value from data GitHub, and you can start putting in your comments. We'll create a wiki or a discussion, and then we can do that. If you have ideas for projects, even if you want to learn something, basically you want to do something, just give a post there. Yeah. Okay, good. So we should do that. Okay, so can we move that also to value from data, or are you doing it on your? Okay. Okay. So you can just post a link, Karthik, for value from data. So we'll start this and make sure. I'll take your help, and we'll make that a kind of a discussion forum for doing that. Okay. So today you have already seen the agenda for today. The first agenda has changed, so he's going to tell you what the change is about. Wow, not bad. We're getting slightly more number of people. Okay, and then of course the final mandate element. How many people are actually looking for jobs in the data science area? Good. All of you see me or give me your email address. You can send me an email, whichever is simpler for you. At the end of it, and because we are looking for building a team, would be very happy for us to kind of start something and then do this, and I'll tell you what we want to do. I'll talk about it since there are only 4 of you. I don't want to bore everybody else with this information. We'll talk privately. Catch me during a break or send me an email, and then we can meet. Okay? All right. So you're going to tell about the modified agenda. Does this mic actually work? Okay, yeah.
Okay. Does just check the audio level. Okay. Okay, can you hear me at the back? Rajesh, is it okay? Okay. Okay, just switch my phone off. Okay. Right. Okay, so if you've seen the agenda, I've changed it completely. You know, I thought I'd do regression and then instead I'm going to do classification because I thought about this quite a lot. And I feel that, you know, from what we've already done in the previous couple of lectures, you know, doing classification in this Bayesian framework is going to be a little bit more natural than doing regression. Okay, and so we'll do regression maybe later. But right now I want to do the classification tasks. Okay, so how many of you have actually done or used a classifier or encountered a classification task? You just raise your hands. 1, 2, 3, 3. Okay, so do I assume that the rest of you don't exactly know what a classification task is? Is that a yes? Would you raise your hands if you think that's a fair statement, that you need to be explained what a classification task is? Okay, fine. Okay, yeah, okay, right, great. Lots of people. Fine. So what I'll do is I'll go a little bit more slowly than I had assumed. As usual, everything is available on the GitHub repository, and my slides will be available there. So what I'll do then is again to just remind you what our general sort of theme has been in this bunch of workshops, that looking at probability as logic and then introducing probabilistic graphical models to look at, you know, complex situations. Okay. So what I want to do now is Bayesian classification, and then Gaurav had suggested we might look at this Kaggle competition where you have this Titanic challenge, which is like a classification task. So in the Kaggle competition, it is suggested that you use a certain kind of classification method. I'm going to try and do a different kind of classification method just to show you how you do it within the framework of these probabilistic graphical models. Okay. Okay. So for those of you who have already used classification, what classifiers did you use? Random forests. Okay. And naive Bayes and logistic. Okay. Fine. So, you know, of these, logistic and naive Bayes and random forest, it's only naive Bayes which kind of falls in within this framework of probabilistic graphical models. Okay, and I will try to explain why I would prefer to do it this way rather than use any of these other two classifiers that have been mentioned. Okay, but before I start, I want to start with this puzzle. So if you've been following my Twitter feeds, you'll see that I've given this puzzle, and you'll see why it is important as the lecture progresses. You'll see what is its what the relevance of this is. Okay. And the puzzle is this. So this is a picture of the IIT campus just around the corner. If you've been inside, you'll see it has a lot of sort of animals. And now the puzzle is this. So I walk into the campus. I see these cheetah. Okay, there are 20 of them. At least I count 20 of them. I see 20 of them. There are not 20 of them. There are many. I see some monkeys, 10 of them. I see some dogs, 6 of them. And I see this black buck. Okay, 4 of them. The question I'm asking now, given all of this data, what is the probability that I see a new species? Okay, so there's somebody from IIT Raj who can answer, who can try his first guess at answering this question. So can you tell me how you would go about answering this question, or can you just even give me an intuitive feel for what you think this probability might be? Just guess. So first of all, is this a well-posed question? Do you have enough information for answering this? Okay, so once. So I went in once, and I'm sort of driving around. I'm starting from the main gate. I'm going, let's say, to the academic area, which is a long drive. And as I go along, I see this bunch of things.
Did you picture all
Sorry? Are these,
all these spaces?
Well,
this is only a subset of what you saw.
This is exactly what I saw. This is all I saw. Right? This is the only thing I saw. I saw 4 species, and these are the numbers that I saw. And now I'm asking you, What is the probability that I'll see something new, something which is not any of these things?
So, first of all, you would have labeled it wrongly. You would have considered something else similar and then put it in teacher. So,
No, I'm assuming all identifications are correct. So if I say I've seen 20 of these things, I really have seen 20 of these things. If I've seen 10 of these, all of these are, there's no mislabeling. Okay, so I've seen all of these things absolutely correctly. Okay, so
on the distribution
of
for the species.
yes, so it depends on the distribution of the species. Okay, but my question is slightly different. So do I have enough information to answer this question? You don't have enough information to answer this question. Sorry?
On the universe.
Huh?
On the universe.
So you want a new species? Yeah? Okay. So if I asked you a separate, so we'll move towards the answer. Okay, so the first answer is, there is actually enough information to answer the question. Okay, although it may look perplexing, there is actually enough information to answer the question. I'll show you how. If I ask you a different question, tell me what is the probability of seeing another cheetal? What would you say then? Cheetal, yeah, the spotted deer. 1 by 20. Why do you say that? Sorry? Why do you say 1 by 20? So there are 40 things I saw, and of them 20 were cheetal. Then what is the probability? It's 20 by 40, right? Half. Okay. So here it seems that the probability of half of seeing a cheetal. Okay. And similarly, this much of seeing the other things. Okay. So I saw 40 things, of them 20 are cheetal, 20 by 40, half is the probability of seeing a cheetal. Or 1 by 4 is the probability of seeing a monkey, and so on and so forth. But then, what is the probability of seeing a new species? If you do it this way? 0, right? That means if I do it this way, there's absolutely 0 probability that I'll see anything new. Okay? So clearly, but I know intuitively that there might be other things out there, right? So I have to figure out a way of changing this naive probability assignment that I do, of taking the number of things I see, dividing it by the number of total things I saw, and assigning that to be the probability. Okay? So I have to think of some better way of assigning probabilities so that this statement has a finite probability. Okay? So this is the question that I'm interested in once I pose it as a Bayesian question. What is the probability of new species given the observed species? Okay? And I want to know what is this. The answer is this. So there is 1 in 1 by 45 chance of seeing a new species. Okay? Now the question is, where did I get this number from? Okay? So it's not 0, it's 1 by 1 by 45. Where did I get this number from? And the answer is I got it from a method called Bayesian smoothing. Okay? Now this is very, very important for any kind of classification task that I do. Because whenever I'm building a model, I'll have to answer a question of this kind. There'll be lots of things that I see and a bunch of things that I do not see. Okay? And if I assign 0 probability to those things that I do not see, my model will be a very constrained and overfitted model. It will not be able to tell you new things. Okay? So let me just quickly go through this thing, and I have to go to the board for this. So is this question, is the question, yes?
So here the observed is like the considered the all
Yeah. See, observed is whatever I showed in the previous slide. So that is my data. So in this Bayesian way of thinking, we have to always condition on data.
This is only one new species or
So let's do that systematically. Okay, so I want to now, so this is a very simple probability problem, but when I show it to you first, it seems perplexing. But once it's broken down, you'll see it's actually quite simple. So we'll see what is the way to break down these questions, okay? And how do you break it down into its component parts and then go about analyzing it? Okay. So the first thing, whenever you encounter a probability question, is to identify what are known things and what are unknown things. That's absolutely critical right at the beginning. Okay. So in this problem, what are the known, what quantities are known? So the number of things that I've seen, let me call them n. Okay, the number of things that I've seen. Okay, so the number of species, let's say. So I've seen I is equal to 1, 2, 3, 4 species, right? So I've seen 4 of these species. And corresponding to that, the number of species is 20, 10, 6, and 4. Okay, this is what I know. What is the question that I'm asking? What is the probability of a new species? New species, right? Now, like you said, I want to know the universe, right? So the universe is composed of what? These 4 species and their complement, right? So if I say A is this bunch of species, so A is Chital, and all the remaining 4 I saw, then A bar must be new species, right? The complement of this must be the new species, right? And what do we know from elementary probability? That P of A plus P of A bar must be 1, right? The probability of all the things I see plus the probability of the things I do not see must sum to 1, right? Now this is the key to solving this problem. When I say new species, it basically means it's the complement of everything that I've observed, okay? And the sum and the probabilities must sum to 1 of these things, okay? Now, what were we doing here? We were kind of, in the first way we did it, we naively said, and this is really, there are, since there are 4 of them, I have to sum, right? So this is 1 through 4, right? So this goes from 1 through 4. So what were we doing naively? We were saying P of Chital, let me call that. So we were first saying P of Chital is 20 by 40, P of monkey is 10 by 40, etc., 6 by 40, and 4 by 40. And these were summing to 40, right? 40 by 40, right? So they were summing to 1. That means this probability is already equal to 1, and therefore this probability is 0. There's no space left for allocating here, right? So what I have to do is, I have to reduce the allocations here and increase some allocation here, right? So that I get a finite answer for probability of the new species, right? Now the whole question is, how do I change this allocation? Okay, so if I draw a histogram, I have here, so this is P of the species, and this is the species itself. I have here a histogram, not very good, not well drawn. Okay, and these histogram bars now sum to 1 in the naive way of doing it. What I have to do is I have to shave off some probability from the tops of these histograms and allocate it to this quantity A bar, right? And now then everything will sum to 1, and now this will also have a finite probability. Now the question is what is the algorithm for doing that? Okay. And once you work through this, you will see that through this algorithm, the amount of probability that is allocated here is exactly 1 by 45. Okay, and some of these probabilities have been reduced, and more probability has been allocated here. Okay, so let's see how we do that. Let's see how we do that for a simpler problem. Very simple problem, which is, again, you must be bored seeing this problem, but this problem is so illustrative that I keep on showing it. Again, let's do so now the question is, so let's decide first of all, what is the sampling problem? Okay, so what is the sampling problem here? I have here what is called multinomial sampling. Right? Not a binomial sampling. In a binomial sampling, there are precisely 2 kinds of things. In a multinomial sampling, there are I equals 1 through k kinds of things. Okay, so here k is equal to 5. There are 4 known categories and 1 unknown category. Okay, and I have to sample from this multinomial distribution. Okay, now the multinomial distribution. So remember the binomial distribution. The binomial distribution is when k is equal to 2. There are 2 categories, head and tail, corresponding to which the probabilities, probability of head is theta, probability of tail is 1 minus theta, right? These are when you have binomial sampling. When you have multinomial sampling, there are probabilities of the categories AI. Let's call them theta I, okay? All the categories that I have. The property that sum P of AI must be 1 translates to summation theta I being 1. Okay? This is a generalization of the theta and the 1 minus theta of the binomial distribution. Okay? So I'm sampling from a distribution in which there are k categories. The elementary probabilities must all sum to 1. And now we just use Bayes' theorem to figure out what is this quantity. So what is the data that you get from a multinomial distribution? From a binomial distribution, remember, you get a bunch of numbers n1 and n minus n1. Right? So if you've thrown a coin 10 times or capital N times, you'll get n1 successes and n minus n1 failures, or n1 heads and n minus n1 tails. Here you'll get a bunch of numbers n1, n2, nk, where again k goes from 1 to the number of things that you have. And these sum of nks must be the number of times you actually did your trials. Okay? So in this case, just going back to this problem, n1 is 20, n2 is 10, n3 is 6, n4 is 4, and nk is 0. Right? I didn't see n5. n5 is 0. Right? And the sum of them, capital N, is 40. Okay? What is the question I'm interested in? I want to know what are the corresponding binomial parameters, sorry, multinomial parameters, theta 1, theta 2, theta k, right? Because if I know these parameters, then I can know what the probabilities are, because these parameters are basically the probabilities of, these parameters are precisely these histograms. Every one of them is one element of this histogram, right? So I want to know what these parameters are. And our naive way of assigning these is n1 by n. Right? This is our naive assignment. So then this is, as we said, 20 by 40, etc., and things like that, and this is 0. Okay. So this is our naive way of doing it. Now, how do we do it using Bayes' theorem? So let me just take this out. So unfortunately, on this board, it's, yeah, well, I'll just keep the screen. Just keep that in view. Okay, so how would we do this if they were, so let's just do the very simple case of the coin, of bound k equal to 2. Because if you understand the k equal to 2 problem, the k equal to any problem is simple. Okay, so in this case, I have a situation where I have only seen heads. I've done lots and lots of throws, and I've only seen heads. And the question is, what is the probability of getting a tail? Right? That's exactly what this problem is, translated to the k equal to 2 case. I've only seen heads, I've not seen this other thing which might be possible. Tell me what is the probability of that thing. Okay? So how do we do this? So in this case, there's this theta. P of h is theta. P of tail is 1 minus theta. And let's do it using Bayes' theorem. We want to estimate P of theta given the data. And this data is this n1, n minus n1. I did n throws, I got n1 successes, right? So this by Bayes' theorem is P of d given theta, P of theta. Numerator is the normalization, P of theta given d, d theta. Yes, this is the normalization. Everyone, I hope, is following. If you're not following, tell me and I'll stop and I'll explain. Right, so this is a normalization. Now, this is given by the binomial distribution. P of d given theta is just P of n1 given theta, and that is capital N choose n1, theta to the power n1, 1 minus theta to the power n minus n1. Right? This we all know, simple binomial distribution. What about this? Now, this is where all the catch is. What do I set for the prior? Okay. So So if you've been doing a little bit of text classification, you'll hear of this thing called the Dirichlet distribution, latent Dirichlet allocation, Dirichlet priors, and so on and so forth. Okay. So what we have to set here is a prior. So this P of theta signifies what is the probability of this parameter even before I have seen any data. Okay. And if you see the form of this probability distribution, this is just a number. What is the variable in the probability distribution? This is the quantity that I'm interested in. This is just a number. So this number, the real variation is in this factor. Okay? This is just a scale. The real functional variation is in this factor. And now what you want to do is, you want to assign a prior, which is called a Dirichlet prior, which has the form gamma. So gamma is the gamma function. Gamma of A plus B, gamma of A, gamma of B, times theta to the power one minus A, 1 minus theta to the power 1 minus B. Okay. So now, why am I doing this? This prior looks like this. So if I look at P of theta will vary from 0 to 1. It goes to 0, okay, at the edges, because, well, it doesn't go to 0 at the edges. You can have finite values, but for the typical value of the prior that is chosen, so maybe I'll just quickly flash this once again here, so that just give me one minute. Yeah. Okay. Okay. So, okay, obviously sign errors here. A minus 1, B minus 1. Okay. Now this is the prior, and this is called a Dirichlet prior. And once you take this and plug it back in here, you will see that the posterior distribution, which is the thing that I'm interested in, okay, looks like, so the answer is, or it's proportional to just this. Okay, so it's theta to the power n1 plus a minus 1, 1 minus theta to the power n minus n1, which is that, capital N minus n1, plus b minus 1. Okay, so this is my answer, P of theta given d. It's proportional to, okay, because I'm not worrying about the denominator right now. Now just stare at this for a minute. Okay, this is my final answer for what I believe this parameter is going to do. What is the value of this parameter? Okay. Now it has these additional parameters which are coming from the prior. These things are called hyperparameters. Okay. The shape of this distribution, the shape of the prior distribution, will look like that if I make the choice. So it will be centered around half. If I make the choice A is equal to 1, B is equal to 1. Okay. So you can make any choice you wish, but for this particular choice, that's what the prior distribution is going to look like. This is what the posterior distribution is then going to look like. And then these things are gone, okay, with that particular choice. And then if I do my expected value, okay, what is the expected value of theta? That's how I quote my final answer, right? So I have a probability distribution, I look at its mean. And that mean is what I say is my best guess for it. I can look at the mode as well. Okay, so how from the probability distribution, how I quote a number will depend on what I'm using as my point estimate. So a probability distribution is a function. From that function, I have to give you one number, which is my best estimate for what the value of the parameter is. Okay. So the general thing to do is to look at the mean of the distribution. Okay. You can also look at the mode, which is the most probable value. So you'll get some posterior distribution, which may again look like this or may look different. may look like that. Now, there are two possible choices. I can look at the most probable value, or I can look at the mean of the distribution. Okay, so the accepted way to do it, again I can tell you why that is so, is to look at the mean of the distribution. Once I look at the mean of the distribution, this distribution, the mean value, is actually n1 plus 1 by capital N plus 2. Okay, so you have to do this calculation. I'm just giving you the answer directly. Okay, once you look at the mean of the distribution, you will see that it has changed in a very important way. And okay, so the general answer is n1 plus a and n2 plus, okay, so I'll come to the general answer in a minute. Let's just leave it like that for now. Okay, so now you see it has changed in a significant way, that from the naive estimate of theta is equal to n1 by capital N, it has changed in a very important way. This way of doing it tells you that you should increase the count of the numerator by 1 and increase the count of the denominator by 2. Okay? And in this way, if you do it this way, you will see that even if you've not seen any number of tails, so let's say n of tail, just switch it, just make it heads. You've not seen any number of heads, then it will still give you a finite possibility for seeing a head, because this is 0, but the numerator is now finite and the denominator obviously is finite. Okay? So this way of doing this, of starting with Bayes' theorem, looking at the likelihood, putting a correct prior, and this is true for any prior you put in. Okay? Whatever prior you put in, this prior will affect the naive estimate, and you will get always a correction like this. Okay? And this general correction of taking the naive estimate and replacing it by another quantity which assigns finite probability to the unseen events is called smoothing. Okay? And it's very important for, it'll come in a minute why it's important. Okay? So in this case you see this is what is going to happen. In the multinomial case, again I'm going to just I'm not going to work all of this out, I'll just tell you how it's different. Yeah, so if stop me now if you have any questions, because I'm just going to, yeah. So the final answer is actually, you're asking what is the final answer if you have A and B, general A and B, right? Yeah, I will just give it to you. Sorry, so let's just see. Is this working? Can you see the whole thing? Yeah. So that is the general answer. N1 plus A, N plus A plus B. Okay. So as I said, I have taken the choice of A is equal to 1, B is equal to 1. Okay. So that gives you the 1 here and the 2 here. Okay. And you can see, so what will happen is, so never mind all those comments are for someone else, but this is basically the estimate that you do. Okay? And this is the estimate that you do, the naive estimate. Because if you see, if I put this in the naive estimate, with A equal to 1, B equal to 1, I'll get the naive estimate. Okay? So with this way of doing it, you can either get the naive estimate, if you're making a certain choice of the posterior, basically the way of reporting, going from the probability distribution to the number that you're using, or you can get the more sensible smooth estimate. Okay? And this basically says, what is the logic of this? All this is saying is that if you have a distribution, so remember there are two things coming in here. One is the contribution. Bayes' theorem always has two pieces. One is the contribution from the data, and the other is the contribution from the prior. Okay? So the data gives you certain information, your prior assignment also gives you some information. This is saying if you have a probability distribution which looks like that, right, and you are using the highest point to make an estimate, this is okay if your probability distribution looks like this, where all of the probability is concentrated near the peak. But if you have a very flat distribution, then the peak is a very poor indicator of what the value is likely to be. Okay, and this is exactly what this is saying. If you take the modal value of the distribution, you will get the naive estimate. If you take the mean, the mean value, it will include all the possibilities that are away from the mode. Okay? And when you have very little data, then obviously your distributions are going to be very broad, and then you should use the mode. You should use the mean. Okay? And this is essentially what is happening here, because in this case you have no data at all, right? And if you make an estimate using the mode, it will be a very wrong estimate. Okay? And this is essentially what this is saying. Okay, so that's the general result. Now let's go to the, so this is called, this formula of increasing the count by 1, n1 plus 1 by capital N plus 2 is due to Laplace. And it's called Laplace's formula, or it's called add 1 smoothing. Okay, there are many other kinds of smoothing as well, but we'll stick to this for the time being. Okay, what happens in the multinomial case? In the multinomial case, I have now theta is a vector because I have theta 1 all the way to theta k. The probability distribution theta given d is now just a generalization. So the n choose small n factorial now becomes n factorial, n1 factorial, n2 factorial, nk factorial. These probabilities become theta to the power n1, theta 2 to the power n2, theta k to the power nk. Remember, all these nks sum to capital N. Okay, the prior p of theta is a generalization of the multinomial distribution, so it's gamma of a plus b plus dot dot. For each of them, I have a parameter. Okay, divided by gamma of a, gamma of b, dot dot, and again theta to the power a minus 1, theta to the power b minus 1, dot dot dot. Okay, and you do that, and you now have to do some tedious algebra. But at the end of the day, so there's nothing different in principle. In principle, it's exactly the same, except that I just have many more parameters. So if you understand the binomial problem, the multinomial problem is just additional tedium. It's not any new conceptual thing. At the end of the day, when you finally get the answer, you can see how the answer is going to generalize from here. Okay, the answer will be each theta I will be given by ni plus something divided by capital N plus something else. That's what the answer is going to be at the end of the day for your estimate for theta I, right? And now, can you guess what these numbers are going to be? Yeah. So it will be 1 here, right? It'll be so you have to increment the numerator by 1, and you have to increment the denominator by k, right? So that's the answer. So it's ni plus 1, capital N plus k. Okay, this is the final answer for a multinomial distribution. So this is the analog of add 1 smoothing for a multinomial distribution. Okay. Now what happens? So now you can see what will happen. So let's just go back to the problem that we started motivating this by. So what do I have? I didn't see any species at all, right? So this is 0, right? So the probability of A5, which is no species at all, new species is A5, and N5 is 0. So the answer is 1 by 40 plus 5. Capital N is 40, K is 5. Okay, this is the answer. Okay, so it's 1 by 45 chance of seeing a new species. Okay, now you can ask whether this is is this a unique answer or is there a family of answers? And the answer is that there's a family of answers, because any choice of A and B I make will give me an answer. Okay, but the accepted choice is to take a symmetric Dirichlet prior, which basically says I'm not biasing myself in the beginning to any possible disbalance of the species. So right, when I go there, I assume that all the species might be equally distributed. Okay, just like when I start my coin tossing, my prior says that heads and tails might be equally likely. Okay, so if I take a symmetric Dirichlet prior, this is the answer that I'll get. Okay? If you have additional information that you know perhaps that some of the preces are highly skewed, then you will put in a prior which corresponds to this. Okay, now.
Like, for example, in this case,
Yeah.
we could give more prior to this 20 or something like that.
So in the case, so if you didn't take A equal to 1, B equal to 1, you would say, suppose you took A equal to 2, B equal to 1. That would move your prior distribution towards heads. Okay? And then you will get a little bit of bias towards heads. And then therefore these factors will change a little bit. Okay? But you started with a symmetric prior, you will get 1 and 2 as the factors. Okay? So even though there's a family of distributions, even though there's a family of answers, there's a well-defined way of understanding what each of those answers is going to give you. Okay? Because that information is going into the prior distribution, and that prior distribution reflects your state of knowledge of what you think of the distributions themselves. Okay? So depending on what you want to do, you'll get an answer. The answers are different, but they're all well controlled. They're not arbitrary answers. Okay. So now you know here, basically this much has been shaved off. How much has been shaved off from each of them? And 1 by 45 has been assigned here. So 1 by 45 has been taken off from here and put here. Okay? Right. So now this is a basic element of a smoothing formula, and you can now make generalizations. What you can essentially do is you change the sampling distribution. Most of the time you're doing multinomial sampling, so this doesn't change. But you can change the priors, and you can get a whole bunch of different smoothing formulae. Okay. Now why am I saying this? So let's try to get back to classification, and it'll be clear why I introduced this in the first place. Okay. Okay, so now this answer is clear. Right? So it comes from Bayesian smoothing. Okay. Now I'm going to tell you a little bit about the classification task that I have in hand. Okay. So for those of you who've done classification, will you just share what things you are trying to do classification on? What did you do classification on?
So we have a set of defects. So I work for fairly technical. So we have, so we do our tools identify defects in chip manufacturing.
Use the mic. You can sit down and use the mic. Yeah. Yeah. Just. Yeah.
So we try to.
Yeah.
Hello.
Yeah. It's working.
So we try to identify defects from a chip. So what we do is we want to identify what types of defects are, or are we going to detect new kind of defect types. So we use. So the problem statement is our engineers have identified few defect types, and then they don't want to do this manual classification every time. So we feed in the data, whatever they have observed, into the classifier, and then use that classifier in a production unit to just do this automatically, binning the defects.
Okay, so I'm going to make a couple of observations. That's very nice. He's couple of things. So you said this, right? Engineers have identified. Didn't you say that?
Yes, yes.
So I'm going to keep that from your talk. That's the most important thing. Gaurav, will you say what classification task you've done?
I did in college. So
Okay, that's okay. Doesn't matter where you did.
The study material what I did.
You want to take? Sorry.
I'm currently looking at the study material.
Oh, okay.
I have the code currently.
Okay. Yeah.
So
Yeah.
the Titanic problem.
Yeah.
Survived or not survived?
Yeah. So will you just explain the Titanic problem, because maybe not everyone's familiar with it.
So the Titanic problem is to predict the survival of a particular passenger. Okay, so they have a bunch of data which is already available. So they have few data points like age, class they traveled, and given that, so we have to come up with a model. And there is a test data set, so where we don't have the survived information. So your model should predict whether that particular passenger survived or not.
So the data set is basically all the passengers who were on the Titanic and whether they survived the disaster or they did not survive the disaster, right? And the question, so the question is, from this, can you...
Sample data, so we didn't
Yeah.
have the data for all.
You don't have the data for everybody, you just have some subset of that. And then the remaining is basically the data on which you must test your model and see whether it predicts it correctly, right? And the attributes that are given of...
So age,
Yeah.
name,
Yeah.
sex,
Yeah.
class they travel, so
Yeah.
cabin, those are the information
Right.
there.
Okay, right. So in both of these things, so this is the example from Sai. Is that okay? Yeah. No, I know that that's the name. I'm just wondering whether that's how you refer to it. You have a bunch of bits in it. Okay, right. So and then I need to get your name. Raj. Okay. So then there's the Kaggle, the Titanic business. Okay. Oh, sorry. Gotcha. Okay. And now Gaurav is not yielding what he has been doing. His classification task he's not telling us. It's secret. Okay. So in both these cases, what you have to do is you have a bunch of, so the general classification task looks like this. You have a bunch of attributes. Okay. Given these attributes, you want to ask whether a particular object is in a certain category. Okay. This is the general classification task. You have a bunch of attributes. You have another quantity which may or may, I mean, which has, okay, I'll talk about that. There is another quantity, and you want to know whether, given these attributes, which of these categories this quantity belongs to. Okay? So in this simple case, these attributes would be the age, sex, name, and what else is given?
Class.
What class they're traveling in. Yeah. So the class they're traveling in. Okay. So age, sex, name, and class of the passengers. These are the attributes. So in this case, there'll be 1, 2, 3, 4 attributes. Okay. And given that, you want to know, did the passenger survive or not survive? Okay. So there are essentially 2 attributes here. So two classes here. Let me call that 0 or 1. You can call it survive and not survive. Okay. Similarly, in size problem, you have a bunch of attributes. Now these attributes could be some part of the domain, okay, some specific things of the image and so on and so forth. And you want to ask whether the sample is defective or non-defective. Yeah. Or is there a third?
Binomial class,
it's a multinomial class. Okay, so there are a bunch of things. Okay, so there are, it's of various categories. Okay, so you want to know this. Okay, so this is the general classification task that you always have, right? So attributes, given a bunch of attributes, tell me which class this thing belongs to. Okay, now the way we do it in a Bayesian way is no different from the general, the good thing about the Bayesian way of doing it is there's only one formula. Okay, so you can only use that formula and there's nothing more to do, and which is why I like to do it this way. So here the probability question that you're trying to answer is, tell me what is P of C given AI. This is all you're trying to answer. I have a bunch of attributes. I know their values. Tell me which class does this thing belong to. Okay, and now how do I do the classification task? Again, when I look at, so assuming I have calculated this probability, assuming I have been able to figure out how to calculate this probability, and this is a discrete problem. Again, I'll get a histogram for each of the classes. Okay, so here are each of my AIs, and this is P of C given AI, sorry, these are the CIs, the C, the various values that C can take. And the Bayesian classification algorithm is to say that I will classify this object with the one with the highest probability. Whatever has the highest probability, I'll say that it belongs to that class. Okay? This is how the Bayesian classification problem is slightly different from other kinds of classifiers. Okay? The other classifier gives you a binary yes-no answer. It just puts it directly into one class or the other. Okay? In the Bayesian classification, it doesn't do that. It doesn't commit to any particular class. It just gives you a probability distribution over the classes, and it is your task to choose what is your final answer. Just like in the coin tossing problem, you don't get a number. You get a whole probability distribution, and it's your task to say which number you're going to use to give the final, quote the final answer. Okay, now this is particularly useful. The reason why it's particularly useful is that when you're doing a classification task, there is often a utility associated with it. Okay, if you make a wrong classification, there is likely to be a penalty, right? If you misclassify, there's going to be a penalty. Now, in the usual way of doing classification, so if you're using random forests or logit or whatever, or something like that, putting in the penalty is not so straightforward. Okay, in logit, it still may be straightforward. In random forests, it's absolutely not straightforward at all. There is no way of saying what is the cost of misclassifying. Okay, so here it's very easy to actually compute what is the cost of misclassifying. Okay, and the way to do it is to say that associated with each classification, I will assume a utility function, or let me just call it a cost. So the cost will be something like, I will have to pay a cost, no, sorry, I've already used C. Let me call that utility, I'm just calling it utility. This utility is going to be something like this. If the category is really C, right, and my classifier is telling that it's C prime, I'm going to pay this much in error. Okay, so if the category is really C and my classifier says it's C, then there is no error, right? It's 0. I don't pay any cost at all, right? But each time I misclassify, I'll have to pay some error. Okay, and the simplest error that you can say is quadratic. So whether I so this is the kind of classifier you use for a continuous variable. So whether the classification is in the positive direction or the negative direction doesn't matter. Okay, I will just pay a cost for it. And what you now do is you say what I want to maximize. So in the other case, what I was maximizing was just the probability distribution. In this case, what I want to maximize is the utility, expected value of the utility. So what I want to do is I want to calculate over all possibilities P of C given AI times C minus the real C minus, so this is, okay, so my notations are a little peculiar. Okay, let me just try to explain to you what we're doing. What you're trying to do is, here's the cost. So there are whole bunches of classes. Each time you misclassify, you pay a quadratic cost, and now you sum this over all the classes that you have. Okay, so this is saying I'm going to pay, each time you make a mistake, I'm going to penalize you, and now you want to find out what is the least penalty that I have to pay. Okay, so this kind of thing can be done within a Bayesian classification scheme, and that is why you can often get, in addition to the classification, you can also get a cost for misclassification. Okay, now the reason I put this up is that most of these classifications are called supervised. That means somebody has actually gone first and done this classification for you. That given a bunch of AIs, where does this class belong to? Okay, so in size problem, the expert domain engineer has first gone and said, okay, if I have these bunch of attributes, then it belongs to this class. In the Kaggle problem, you've taken part of the data set out. You've said, given that these guys have these attributes, they survived or they did not survive. Okay, so in all of these problems, there is an available data set where this mapping from attributes to the category has been done for you. And your job is to figure out from that data set, when you see a new data, how are you going to do this allocation? Okay, and now this is called supervised classification. It means that somebody has to tell you something to do. The algorithm is not so smart that you can just throw the data at it and it will pick up the answer. Okay, somebody else has to give you a model for it, and then the algorithm can go and learn that model and then predict newly. Okay, now how are we going to do this? So all the examples that I'm going to talk about will be in this supervised classification category. That means you already have a data set. Now, I finally want to make this connection now with Bayesian networks. So let's take the Kaggle problem because it's a little easy to understand. P of C given AI. This is what I want to know. Okay, this is the object that I want to know. Yeah.
So actually I use this GLM made for detecting spam detection using GLM. So is it related to this Bayesian classification? General linear model.
General linear models. Yeah. Okay, so my answer is any probabilistic model can always be fitted into a Bayesian model. Okay, just how you do it is the trick. Okay, so you can do a GLM as well. Okay, so let me just show you for the Kaggle problem how we'll go about, and then we'll figure out all the other ones. Okay, so in the Kaggle problem, I have this bunch of things. AI is equal to name, gender, age, and class. Okay. Now this is where the Bayesian modeling is a little different from the general other kinds of modeling, because I want to think of this as causal. Okay. So from this bunch of things, which do you think is probably the most important? Age and class.
Age and gender also.
Gender, age, and class. Do you think name is important at all? What your name is, does that depend on whether you'll survive or not? Okay, so when we look at data, we already have a causal understanding for it. Okay, and these probabilistic graphical models help you build that causal understanding. Okay, so in this probabilistic graphical model, what we will say is that this C, so this is the class, okay, and this will take on values, survive, did not survive. Okay. This has arrows going down. Now these arrows represent name, gender, age, and class. I'm sorry? Right? And from our last class on probabilistic graphical models, you know that this object represents a conditional probability. And this represents precisely this conditional probability. Okay? So now I have, now look at this. What am I saying here? This is actually building a causal model. This is saying that there is a causal link between all these attributes that I have and the classifying object that I'm interested in. Okay? And these are all conditional probabilities. Okay? There are no links between these variables. Right? There's no link which is connecting them. Right? That means all these attributes are independent. They're not causally connected to each other. Okay? This is when I do a model like this, where the class that I'm interested in is sitting at the top, the classifying object that is sitting at the top, and coming down, all the arrows are all the attributes that I'm interested in, and there is no connection at all between any of the attributes. An object like this is called a naive Bayes model. So what is the naive part about it? The naive part about it is none of these guys are actually correlated. They're not causally linked. Okay? They're all independent. So when I make this independence of attributes assumption, such an object is called a naive Bayes model. So the naive comes from this independence of attributes assumption. Okay? Now, what is given to me in the supervised data set? What is given to me is the opposite thing. P of attribute given C. Right? This is precisely what is given to me. I know if a person survived, I know their name, gender, age, and class. If a person did not survive, I know their name, gender, age, and class. Right? And now what I have to do is, so I can go to my data, I can find out for a person who survived, what are the distribution of these things. Okay? And I can assign on these arrows conditional probabilities. P of name given C. P of gender given C, P of age given C, P of class given C, right? So for each of these links, there will be two such arrows. One is for the survive, one is for the did not survive. Survive, did not survive, survive, did not survive, etc. Right? So how many probabilities are there? How many probability tables are there? So 2 here, 2 here, 2 here, 2 here, right? So there are 8 probability tables. There are 8 conditional probability tables, right? Now, given all of this, what is the question I'm asking? I'm saying now, let me come to a new data set. So this is, I have now built my probabilistic model for this. Given the data that I have, this is my probabilistic model for this. Now I come to a new data set. You give me someone's name, someone's gender, someone's age, and someone's class. And the question is, go up, go against the reasoning. Tell me what is the probability distribution of this. Okay? And that's essentially just using Bayes' theorem here, saying that going from P of AI given C to P of C given AI. Right? So the first part is, I go to my data set, I learn all these probabilities, and this is where the smoothing comes in. Okay? Because I have to learn, if I saw that, let's say hypothetically, that anybody who was male always survived. Let's say hypothetically I saw that. Then I would assign here on this link a probability of 0 for survival if you were female. Right? And that is why it's precisely under these conditions that you always have to do smoothing. You have to say, even if I saw every man in the ship surviving, that still does not mean that men cannot sink in the disaster or whatever. Okay? So all these unseen events that you have to account for them, and typically you will always see that this is a very important part of the exercise of imputing these probabilities. Okay? So you have to, whenever you're doing this imputation from the raw data and you're assigning these probabilities, always have to smooth. Okay? So this is basically, so the chain is data, you do the smoothing, and then you get all of these probabilities. Now your network is built, your probabilistic network is built, and now you can do the simple instantiation of the network, assign any variables that you ask, and you get this number. Okay? This is the way to do it if you're doing a naive Bayes model. Okay? Now, for anyone else who has encountered this problem, how would you do it? How would you do it? Okay, so just, I'll give you 1 minute. So does this seem intuitive? Does this seem reasonable, like a reasonable way to do it?
Normally in our brain, we used to create a model.
Right? And this is basically what you're doing, right? So if you now plug it into a random forest, do you know what is going on inside? Okay, a random forest classifier, let's say.
Here we know that the attributes have got few, like name doesn't make sense, but every time it might not be the case for different problems.
Right, sure. I'm coming to that. That aspect I'm coming to. I'm coming to that.
If you don't have any prior information about the data.
I'm coming to that aspect, yeah. That aspect can also be taken care of. But I'm saying, for this problem, so when I think someone suggested that we'll do the Kaggle problem, and I looked up this particular problem, and it said do it using random forests, okay? And then I said, this problem, trying to do it using random forests doesn't make sense. It just completely, unintuitive. Whereas if I use a naive Bayes classifier here, it's at least intuitive, okay? And then we can try to see how to improve the naive Bayes classifier, and that's what I'll talk about in the next 15-20 minutes. Okay, how do you go beyond this very naive assumption? So you wanted to say how you would do it?
What we did was we did some data analysis and found out, okay, so decision forest also helps a lot. So that was easy to understand. Then logistics, so decision forest was easy to understand.
Yeah. So the decision forest is kind of in this spirit.
Almost.
Yeah, it's in this spirit, kind of in this spirit. But again, with the decision forest, I don't know whether you can do misclassification penalties. So you can't do misclassification penalties there. Okay. So there are other algorithms. Okay. But my first port of call, whenever I'm encountering a problem, is to think in terms of a Bayesian method. Okay. And this is. Yeah. So it's just so the distinction between forest and tree is the way you're allocating the nodes. Okay, what is the topology of the nodes? Okay, that's just only the difference. Okay, so in this particular case, whenever you see this structure, guy sitting at the top and a bunch of things at the bottom, that's a naive Bayes model. Okay, and now we can try to see how we can improve this model. Okay, so this thing, for instance, we can, in the afternoon lectures, in the afternoon session, we can actually try and see how this works. Okay, we can actually set up these numbers, use the smoother, calculate the numbers, assign the probabilities, and we can use that pomegranate library to set up the conditional probability tables and just see how it works. Okay, and the Kaggle challenge is still open. So if you get some data, you can just submit it and see how you do on the tests. Okay, just a naive Bayes classifier. Okay, I bet you it'll do pretty well compared to most other. I mean, it'll be close. Okay, right. Now let's go ahead and see how we can improve this model. So now, so I was saying that name is unlikely to be a particularly important.
Some
Yeah.
wastage for the attributes, because we obviously know that name is not a.
Yeah. So that's exactly the bit I'm coming to. Okay. So how do I now go beyond this? How do I improve this thing? Okay. So first of all, the thing is that not all the attributes may be important. Okay. So then it may be true that instead of you will get as good a prediction if you actually just delete this node. You say that I don't care, I am not interested in this variable. Okay, I'm not interested in this attribute. I'll only look at this bunch of attributes. Okay. Now, in this particular problem, you understand how the causal model works, right? But in a general problem, when you have a whole bunch of, sort of whole table of columns, and you don't have either the tables are too numerous or you don't have sufficient domain understanding, then you have to go and ask, how do I chart this out? Which of the nodes, if I'm doing a naive Bayes classifier, which of the nodes are important and which of the nodes are unimportant? How do I choose that? So there are several algorithms for choosing that, and that has to do with what is called parsimony of explanation.
It's like opposite of smoothing, right?
Sorry, say that again?
It's like opposite of smoothing, because you are deleting smoothing you rather than.
No, okay, it's slightly different. In smoothing, all you're doing is you're saying that, look, okay, so in smoothing, you're not changing the structure of the problem. Okay, so when you look at a graphical model like this, there are two issues. One is the structure, the topology of the nodes and how they're connected. Okay, that is one thing. The other is actually the numbers that you assign here. Okay, so that is another very nice way of why these probabilistic models are nice. Because this thing, let's put this link back, even before I have given you any numbers, even before I allocated numbers here, you've already told me just by looking at this model, I can make some guess as to what its overall structure is, what its causal structure is. Putting in the numbers is now quantifying that causal structure. This is my qualitative causal structure. Once I put in the numbers, I get a quantitative causal structure. Okay? The issue of putting in the numbers is where the smoothing is. Okay? This is changing the topology. This is changing my belief of what the qualitative structure is. Okay? They're slightly different things. Okay? So that is just putting in a quantitative number. This is actually changing the problem qualitatively itself. It's saying that age is not an important criterion. That's also a very strong quantitative statement, as a qualitative statement. Okay. So now there is this whole question of parsimony. And this parsimony basically says that I must try not, so this in this literature, this is called the Occam or Occam, depending on how you spell it. Occam razor. Okay, so there's a razor which is supposed to shave off unnecessary things. Okay, and this is basically saying that this is how Occam said it. So Occam was a friar, a sort of monk, a Christian monk from the 13th century Europe. This statement was in Latin, so I'm just giving you the English translation, or at least a sort of rough English translation. So basic point is saying is that Do not add unnecessary explanatory variables if you already have a small set of explanatory variables which already gives you the effect that you're looking for. Okay, now how do you, so this intuitive principle that, don't add anything which is unnecessary. This intuitive principle, the way you sort of make it quantitative is to say you compare. So how would I now do this? What I would do is, I'd now take this model. Let me call this, okay, so let me take this model with the age. Okay, and let me call this model 1. And I take another model without the age deleted and call that model 2. So I now have 2 models for the data. Okay, and they differ qualitatively in the fact that, here I've only taken 3 of them and the other one has 2 of them. I learn both the models. So I again go to my data, I do this exercise, I put in all the probability numbers, and I learn both the models. Now I take this model, and I take this model, and I go to my test set. Okay? And then I see how well am I predicting this model against this model. Okay? So now what I want to do is, I want to calculate. So now what I go to the, so I've got my training set, where I have all the, from where I learnt all these probabilities. Okay, and now I go to my test set, which is the place where I want to do the prediction. Now, the data in the test set is also known. Everybody knows what the correct answer is in the test set. It's not an unknown data set. And then I calculate how well this model does against how well this model does. Okay, now there are measures of model performance. Now, that is a whole ball game altogether. What measure you use for model performance? One measure is what is called, coming from the electrical engineering literature, it's a ratio of the false positive to the false negatives. There are other models, Bayesian models of performance, which are called entropic measures. There are a whole bunch of models. So basically, what you try to do is, and so the Bayesian models, what they do is they penalize complexity. So if both these models are giving me roughly the same performance on the test set, and I have another model which has 5 more nodes, this Bayesian measure of that Occam razor will actually say that no, just delete those nodes. This model is not good. So now what you'll get is, once you do this exercise, you'll get a probability distribution in the space of models itself. So you'll get probability of model I given test set. You'll get a probability distribution in the space of models. So this is now P of model given test set. And then you can choose the most probable model. Okay, now how do you get this probability distribution? This probability distribution you get when you use this sort of entropic measures of probability. Okay, so maybe I'll show this in the an actual model performance where you can actually delete nodes. I'll show this in the lectures in the afternoon, in the training session in the afternoon. It's not really like that. It's basically the performance. So I said that there's this utility, right? That if you misclassify, you pay a penalty, right? So that penalty you want to, so the model which pays the least penalty is the best model in a certain sense, right? But now that has a problem, because I can keep on adding more and more nodes, and each time I can make a misclassification, I can add one more node, to fix it up and things like that. And by adding a very, very complex model, I can get a model which has no penalties at all, which is always classifying correctly. But what Bayes' theorem is saying is that that is not your best model. You should rather work with a simpler model. There's a trade-off between the penalty that you pay and the complexity of the model. Okay? You cannot make an arbitrarily complex model which gets everything right. Rather, you are better off making a simpler model which sometimes gets things wrong. Okay? So this trade-off between what is the utility, the cost you pay for misclassification, and the complexity of the model, once you balance these two out, you get a histogram like this on the space of models itself.
And what is this causes must not be multiplied?
Yeah, it's basically saying this, that if you now see two models, so if you say the model without the age and with all of this stuff, and both of them are giving you roughly the same success rate in the test set, then you delete this. So if let's say you get 95% success rate with this model, and let's say you get 96% success rate with that model, depending what your model is, the Bayesian method will actually penalize this model. It may actually penalize this model, even though it's giving you higher probabilities. Okay? Because this is saying, okay, so let me make a fair statement. If both of them are giving 95%, then it will definitely say that this model has 0 probability. Okay, so if you're getting equal success rate with a model like this and a model which has got age, then you know obviously intuitively that this age has no importance. Sorry, the name. Then you know intuitively that the name has no importance. Whether you put it or not, it's not making any difference. So you'll obviously delete it. This intuition, how do you build it into an algorithm? Okay, and that building in of that algorithm is through what is called this Occam razor. Okay, that is the Bayesian way of implementing this intuition that if you get the same performance with 2 nodes and the same performance with 5 nodes, you're better off with the model which has 2 nodes. Okay, I'll explain this in detail in the afternoon. Okay, so this is one thing. Now, so this is a naive Bayes model. How do you go beyond naive Bayes? So you can do naive Bayes with, so once you apply a utility function to the network, the naive Bayes can be sort of contracted. Okay, so you might start with a whole bunch of attributes, and even with naive Bayes, you might want to chop off some of these attributes once you apply an Occam razor to the model. There are several other directions in which this thing can go. One of which is to add connections between these variables. Okay, now there may be a connection between the name and the class you travel in. Now just think about this. Okay? If your name is Sir Francis James or something like that, right? It's very unlikely that you'll be traveling 3rd class, right? So there can be, and if your name is, I don't know, Joe Smith or something, it's unlikely that you'll be traveling 1st class. Okay? So there can be connections between the attributes. Okay? And if you neglect those connections, you will be doing a poor job. Okay? Now, the simplest way of going beyond naive Bayes is to say that these attribute features that I have, some of them may be connected.
Question.
Yeah.
So you said the connection between name and class
Yeah.
will not surface in class itself. It's only you can use it only when the class data is missing, right? So if there is a connection.
Yeah.
Anyway, class we are getting the data of the class also.
Yeah.
So still, even if there is a connection that's came in this derived data that is given. So don't you have a
So you're saying, is it redundant?
Yeah, isn't it?
No, it's not redundant.
Okay.
It's not redundant. Okay. The fact that there are, so the thing is that you what you did in the naive Bayes estimate is that you assume all of these are independent. Okay. So it's like saying that P. So what I did in terms of probabilities here is that I said P of C given AI is P of C given A1, P of C given A2, P of C given AK. This AI is a whole bunch of joint probabilities. So this is P of C given A1 and A2 ... and AK. Right? And I factorize this thing into each of their component parts. Right? Now, this factorization, and therefore the final probability that I get will depend on this, whatever I do on this side. Right? So this factorization basically is saying that there are no connections. Right? And the moment I see that there are connections, say between name and class, this factorization is incorrect. Right? So there will actually be a probability here which says probability of C given AI and AJ, supposing I and J are connected. Right? And this is not equal to probability of IA into probability of AJ. Right? So I'll be making a numerical estimate error here, right? And that will reflect in the classification task I do. Okay. So to answer your question, often it is not intuitively obvious whether the question you're asking. So I cannot give you an intuitive answer for your question. The answer is when I actually algebraically factorize the probability, I'll see that these two things are inequivalent. Okay, so you're saying that, can I intuitively say that whether, once I have class and name and, yeah.
When you are given a data set,
Yeah.
they gave you the actual class. So it
Yeah.
doesn't matter, your intuition about the name versus class is only if you don't get the actual class data. In which case you can say, okay, if this name is higher probability of somebody with surname being in a higher class, is the theory, right? Is the assumption that you're trying to make. But you actually got the class data.
Right.
This person was in this class.
Yeah.
So in which case, the name class dependency is kind of not, at least for this problem, is not important, right?
Yeah, okay, yeah. So in this particular problem, it may not be, the causal explanation may not be exactly important. But, there are whole classes of problems where the attributes themselves are correlated.
Yeah.
Okay?
Here, gender and age is, if you look at the data, you see there is a lot of correlation between gender and age, survival of gender and age. This is female and if they are 35, the survival rate was high. So we have to consider all hormones that are connected.
If we take
No, I understand
No.
the connection between, yeah.
No. So this layer, once you're here, this layer is not got to do with whether it's going up. It's got to do with, is there a connection between your gender? If your gender is so much, is there any connection to your age? So supposing it happened so in the Titanic, this thing that the only females who were traveling were accompanying the males, right? Maybe, I don't know. So, then you would have an age distribution on that. Okay, so if they were all sort of newly married on their honeymoon, they'd all be young women. Or if they're all, parents, old women, or whatever, or something like that.
another real-time example is identifying the fraudulent of a fraud.
Yeah,
So for example, in a specific region, if it is identified one time, okay, in this region, if a transaction is happening, then it is a fraudulent card.
Right.
And so like that, we can do the classification. In that case, the interrelation between the attributes can be made easily. But here we are finding little difficult to correlate from one attribute to other attribute.
Right.
But in the finding the fraudulent of a
so what are the attributes in that case?
so it is, we can define multiple attributes.
Okay.
We can,
Oh, okay. So you're saying that you have a whole bunch of, so that's typically the case. So you have a whole sort of huge family of attributes. And if you assume that a priori that they're independent, that may be quite a strong
for
assumption to make.
example, guy is normally doing transaction in shopping malls or supermarkets or some
Yeah.
other things. But
Yeah.
suddenly he is going to the jewelry shop.
Yes.
So there is some problem.
Right.
People can identify.
Yeah.
Some correlation they can do.
So the basic point I'm trying to make is that if you assume a priori that all your attributes are independent, that's not such a good assumption to make. Okay, that's the bottom line, really. And therefore you can so that is the bottom line. Now the thing is that how do you connect all of these attributes? Okay, so to go beyond naive Bayes, there is a whole family of ways of doing that. Okay, and one of the simplest things is what is called this tree augmented naive Bayes. What that does is, it says that I will only assume that there are links like this. It basically means that I will not assume that downstream I have a situation which can do that. This kind of thing I will not assume. It basically says that every node has as its parent the classifier node and at most one other attribute node. Okay, so I'm imputing very simple structure to the correlators, to the correlations if there are any correlations. The parent node is always the classifier node, and in addition, one attribute node. Okay, this is why I get a tree structure. Okay, so I have a tree here. Okay, and this is called tree augmented naive Bayes. And now you have to immediately ask, how do I know what is connected to what? Okay. Again, so when I'm making an independence assumption, that's trivial to make. I assume everything is independent, so I just draw arrows downwards. But when I'm going to make an assumption of statistical dependence, how do I know what is connected to what? So I might know it in a particular domain case, but in the general case, how do I know what is connected to what? And this is where a new aspect of probability theory comes in, or of Bayesian networks comes in, which is structure learning. So far, what we had been doing is, we had given you the structure, and we were just learning the values at the links. What are the probabilities that I should assign to the links? Here, a new problem surfaces. The moment you add this layer of complexity, that I'm going to relax the naive Bayes assumption, you're immediately confronted with the question, how do I connect up these things? Okay? And so now I have this problem of learning the structure of the network itself from the data. Okay? And that's a very interesting and very cool problem. And this is where really the power starts showing. You give the data, there will be a measure of network complexity, and the probabilistic graphical learner program can actually learn the structure by itself. Okay? And it will learn which links are actually the way it should be connected. Okay? So the structure learning is really the most important thing when you're doing research in probabilistic graphical models. Everybody is trying to figure out how to build better and better algorithms for structured learning. Okay? Because that's where it becomes really important and powerful. Okay, so this is tree augmented. You can keep going. You can have downstream a full Bayesian network. So you have here an arbitrary Bayesian network, etc. So this thing is, and so these are called general Bayesian networks, okay, GBNs. Okay, but there is still one. So I'm going layer by layer. So the simplest layer is naive Bayes, where everything is just like that. Then you have tree augmented, where you have things like this. Then you have this general Bayesian model, where the attribute nodes can form a general Bayesian network. You can have arbitrary connections with them. And at the final level of complexity, you relax even this thing that we have made, that the classifier is actually always a parent of everybody. Okay? Now, in the most general case, what you say is the classifier, the way you set up the nodes is like that. Okay? So it means that the classificatory variable that you have itself can have parents. Okay? So the attribute need not be a child of the classificatory variable. It can actually be a parent. Okay? Yeah, I'm coming to that. Okay. So it can be a parent as well. So the important thing here is that then you have a completely general network. Okay? You have a completely general network, and this looks very intractable, like it's complicated. However, there is this very important concept called the Markov blanket. What is the Markov blanket? You take your node, you look at all its children, you look at all the parents of the children, and you look at the parents. So parents, children, parents of children. Okay? This bunch of nodes forms what is called the Markov blanket of the node that you're interested in, and the value of the node only depends on the state of the Markov blanket. Okay? So now this is very interesting, because what you can do is you can throw in, and this answers the question that you're asking of, what are the sufficient number of nodes. You can take a general Bayesian structured learning model, learn the structure of the network. You can throw in as many variables as you want, learn the structure of the network, but then look at the variable that you're interested in, identify its Markov blanket. Now, its Markov blanket is precisely those nodes which influence the classification node. Okay? None of these nodes have any bearing on the state of the state of the node that you're interested in. Okay? Once you've identified the Markov blanket. Now, each of these is like one of these things. Some attribute which is exhaustive and mutually exclusive.
It need not be combination.
In the sense?
In the sense, like if there are two correlated attributes.
No, these are so each of them. So the correlated, for instance, if you look at the correlated attributes, these two are correlated attributes. Yeah. So everything is modeled here. So here you start with a completely general network. You just say, here are my variables. Give me a network. Give me a probabilistic graphical model which best explains the data. Okay? That will build for you. See the difference between this model And this model is, you assume that the attribute is a common cause. Okay? This is the way you're setting up the model, right? But you could have, so I'm going to think about that. I'll give you the example in the afternoon. I'm just not able to immediately come up with an example where you have this kind of situation, but I will look it up for you. Okay? So here you're assuming that everybody is descending down. But in the general case, that need not be the case. You could have a classification task in which it has parents itself, right? And then you need to know the state of the parents as well. Or even if you don't know it, at least need to model the state of the parents. Okay? But the good thing about this is that if you have a network which is reasonably well behaved, or if you have a problem which is reasonably well behaved, then all the variables that you have thrown in, the network itself can cull from that a subset of the variables. And that subset of the variables is exactly the number of variables which sit inside this Markov blanket. Okay? And why is it called the Markov? What is Markov about it? It's got to do with the fact that it's the conditional independence. Given the state of these nodes, given this blanket, the state of this node depends only on these guys inside the blanket and are independent of the guys outside. Okay? So this tells you what are really, so in this case, if I were to do this using this kind of, if I went to this problem, I would not even assume something like this. I would just put this as an additional attribute, survival. I just add survival to my list of attributes, right? I build a general Bayesian network for it. And then go to the attribute variable, so go to the survival attribute node, find out what its Markov blanket is, and then just look at the state of its Markov, look at the state of the variables within the Markov blanket to use as a classification task. Okay? So in this case, I have somehow taken that out specifically, thinking that there's a causal, this is the classification variable and it is kind of connected like this. Okay? But that assumption I need not make. So this is my, so my general framework is I take all the variables that I have, I construct using structured learning algorithms, a probabilistic graphical model for it. I go and identify its Markov blanket, throw out all the other variables that are outside, and then use that as a classifier.
We could actually use only those attributes again to build right?
So then you can again take, so then your graphical model has now been constructed. So then you throw out everything.
So in a way we identified only the good number of features.
Exactly.
So this could be a feature extractor.
You could also think of it as a feature extraction algorithm if you wish. Okay? Now the difficulty with this is when I actually went to implement it, is there is absolutely very few good libraries in Python which do this. Okay? So there are libraries in Java, there are libraries in Lisp which do this kind of thing, and Lisp is really a different space altogether, So, so there's actually a big opportunity here to actually build a good Python library which will do automatic structured learning, which will identify Markov blankets and things like that, and that's something that Dora and I have been talking about, that, there's this really great opportunity here to do this kind of thing. So we can talk more about it. So I think I'll stop here. This is where I want to stop. So as sort of giving you a general overview of the classification problem. We will try to look at the Kaggle data in the afternoon, and then let's have some tea, and then Dora and guys will tell you about pandas, which is really cool.
Okay, a couple of things while we are setting it up. My email ID is Dorait, DORAIT @gmail.com. So you can send me, there are two things that you can send me. One is that, if you're interested in working on some projects and stuff like that over the next couple of weeks, you can, or if you're, okay, first one is if you want to make any presentations. I know that somebody already sent about sentiment analysis to Ronojoy. We will start slotting presentations from next workshop onwards. First thing is that we'll do the next one next week. Normally we do once in 2 weeks. We'll do the next one next week, and then we'll do the final one probably the week after. That will let you know next week, so that you all know going out of here itself whether you can, when the next one is going to happen. So we'll try to kind of wrap it up. Some of you might have missed when I was saying in the morning that we're going to shift, once we finish the workshop series, we'll shift to what is called a meetup mode, where we'll meet one evening, couple of hours, and then we'll talk about problems. There are a lot of questions that are coming up, so we'll generally discuss those kinds of things, and which need not be in a classroom or workshop mode kind of stuff. That is the second one. Third one is that I said if you are looking for, there are a lot of people who are asking for people with data science or skills and all that sort of stuff. So if you want, you can send me an email, include your resume, and tell me what you want, and I'll try to figure out how to help. We ourselves are trying to find a few people to build some products as well as some applications, and form a consulting team. So love to hear from you. And since you've already gone through like 4 or 5 weeks of these kind of stuff, and it'll be really good to do that. So what we're going to do is, what happened? Works? Demo it is. Which one? Yeah, we can do that. But we just projected a couple of minutes ago. Do you want me to do that? It's working. Okay. All right. So we're going to talk about, I'm kind of mixed feelings about this particular session, right? These kinds of sessions. These are skills that you can actually learn on your own. In fact, most of us, when we come and teach, we learn it slightly before. There is no big theory or anything like that behind that. But I think it's useful to get kind of a overview of what are the things that are available for you to do. So we decided to do, I always ask Ranajai, what do you want me to cover in the Python session? And he gives me some ideas, and we discussed last time, and he said pandas. So we just went and explored it. I did a little bit of reading, and then Faisal did some work. So we're going to split the session. I'm going to just walk you through some fairly simple initial ones so that you get an overview. If you want to actually cover all the things that Pandas supports, you probably require like 3-4 hours. And it'll also be not that interesting because it'll be kind of boring. There are a lot of good tutorials. There's a good book, and there is also a good presentation. So do you have internet connectivity on there? Yeah. Okay, all right. So, so I'll show you the presentation, but I may or may not walk through every one of the slides in the presentation because it's not mine, but it's by a really good guy who wrote a book on Python for data analysis. We'll wait for this to show up, and then it's fairly straightforward. You just go to SlideShare and look for pandas, and remember to put Python next to it, otherwise you'll get very interesting pictures there. Okay, so let me do this first, and this is mine, right? Yeah. Okay. How do I turn off? I want to turn off all the results.
Okay, clear all cells. Output, all output.
All output.
Yeah, clear.
Okay.
Yeah.
Okay. Can you all see this? Okay. So I'll walk through this first. Let Faisal do his demo, and if you have some time, I'll take you to the presentation, which will give you a summary of what are all there that's in pandas. So when I first looked at it, and I said, wow, this looks pretty cool. And the term that they use called data frame actually comes from the R world. And R is very, very famous for data frame. And pandas has a data frame. And I was trying to wrap my head around what is exactly is a data frame. It looks like a table, which is fine. But it's a little bit more than a table because you can do lots of interesting things with it. So we'll walk through some of these things, and they are all, I was just trying to figure out whether it is mine, and yeah, it is mine. So, so you start out by importing pandas, and this is a convention. Pandas as PD and NumPy as NP, and everybody uses the same thing. So there nothing much really happens there. then what you do is you can create a very simple data frame, okay? And then you can create data frame in a variety of ways. You can create it from a list of items that you provide. You can provide it, create it from a dictionary, and I'll show you 2 or 3 of those methods. You can create it from, you can import stuff from CSV file. You can import it from HTML, and you can do all kinds of things in there. So you create a data frame, which I'll just step through and execute. And then you can just print the data frame, which is fairly straightforward. In this case, it's just like 1, 2, 3, and it says column 1, and then it just displays it. And you can, so it's like, think about it as an in-memory array. So the data frames, there are 2 major data structures in pandas. One is series, another is data frames. And actually, you can do some very interesting time series analysis, even though we don't do that in any of the examples. Yeah, yeah. Okay. So what I was doing, I was reading this book on Introduction to Pandas, and I was just typing some of these examples in the IPython notebook to see where it works. You can create 2D arrays, and there is the next one is a bunch of setup. Which will not have any visible effect, but it'll control certain things that happen. In the data frame, you can do, so you can use the numeric NumPy, and then you can create arrays using. So pandas mixes usage of all these things, NumPy, matplotlib, and those kinds of libraries, and you'll see some examples of that later. So I'm going to rush through this because there is nothing much. The statements are fairly straightforward. We don't want to spend a lot of time on the syntax. And then you can do, you can create a series of objects. And the series objects are like, you can simply say from 10 to 15, I want to create a series. And then it will create a series of 10, 11, 12, 13, 14, 15. And, and you can take multiple of these series. So each series is a row with multiple columns, and then you can take multiple of these series and you can create a table. And that's basically what this does. You can look at this. In which one of these cases, stop me if you want to dig down a little bit into deeper, but essentially these are all straight out of the book, fairly simple ones. You can also create a data frame from a dictionary. The dictionary can be like, if you print a dictionary, you'll see like C1 is S1 and column 2 is S2 values. And then you can take this, you can create a data frame from this. Of course, I'm not displaying anything there. So now you start getting into something slightly more interesting. So I have some text which I just grabbed from, I think, Wikipedia page on data science. So this has got nothing, this part of the code, the one that we are looking at, this has nothing to do with pandas itself. You simply take the text, you split it, and then you print the words. And this just want to show you that stuff. So I'm now bringing in text. So far, most of pandas mostly talks about numeric arrays and how to compute and how to group and how to sort and all that sort of stuff. So we also wanted to play around a little bit with the text. So we split the text, and I mean, it's not a great split because we're not taking out all the punctuation and all that sort of stuff. Then I take this entire information, load it into a dictionary, slightly unPythonic code, but you look at this, you create a dictionary. And then from the dictionary, you create a data frame.
This is doing a word. What is it doing?
Sorry?
It's doing a word count.
Yeah, it's basically doing a word frequency count. So let me go back a little bit into the code. You create a dictionary, and then you already split the text. So and it creates a list called words. So we go through each word. If it's in the dictionary, add 1. If it's not in the dictionary, here. So I simply say pandas data frame, just pass on the D2, which is the dictionary here, then it creates a data frame. Then I print out the first 10 items. And when it creates a data frame, what it does is it actually takes it and then horizontally creates the whole dictionary is like, like a row of data kind of stuff, because you can have multiple dictionaries also in this. So what I do is I do a transpose, which turns this into so I'll take the so if you look at the command, it takes first 20 items in the dictionary, and then it slices it and then transposes it where you get all this frequency. Then you can do a bunch of things, like you can sort it, and you can this is sorted, so you can sort it by different orders, by ascending, descending, by different kinds of things, and you can do that. So this is one way. So I have some variable which is a text. I took the text, I split it, I created a dictionary, I took the dictionary, created a data frame. Now I can manipulate the data frame. You can also bring in data from outside. So what I did was that read CSV is a very, very interesting one. You can also do read HTML. I think there is even a read PDF, even though I have not tried it. So there is some Sensex data. I went and collected it. I mean, it was there in some table. I downloaded it. Thing. It's called table.csv. So I import that. And then what you can do is, this has got like a really neat function called head. So what head does is it takes the Sensex data, which is a table, and then it prints out and the top 5 items. You can also do a tail, which is like gives the bottom 5 items kind of thing. So which is straightforward Python. You can also select. So once you have, when you import a CSV, if the CSV has a column names on top of it, and I think Faisal will show you something where you can name the columns if there are no columns. It'll take that as title. These are stock, Sensex values on various dates. So you can actually do some kind of time series analysis on this. What is the open value? What is the high? What is the low? What is the close? What is the volume? And what is some adjusted close? I don't know what the adjusted close is, but this is Sensex data. So you can take this, and I can even select, instead of trying to taking all these columns, I can take a slice of the table. So I can take a slice of table vertically by doing some, using the slice operator. I can say from item 5 to item 20, I can get a slice of 15, which will get 15 rows. Then I can get a slice of columns, any number of columns, by naming the columns. And I think there is also a way you can slice them by the position of the columns. So it's a really good in-memory table data manipulation kind of stuff. And then you can then use this data for a variety of purposes. Okay. So there's a length function which tells you how many items are there. We are dealing with only a small number. Then you can create, it provides you an index into all these items. Index function is so you can externally index items, and which is, I think, very, very interesting if you are doing a class of applications, which may be even slightly beyond numerical computation, because there's a good data structure. So if you're writing a search engine or something like that, and you want to have indexed data structures, and then you want to go and or refer to things, so this is a pretty useful function. So the next thing we do is our favorite example of dealing with jobs. So what we did was we collected a whole bunch of jobs from Indeed.com. We have a cron job, right? Which keeps running, goes to Indeed.com, keeps on getting jobs from .NET developers, Java developers, data science developers, and all that sort of stuff. And then we occasionally take snapshots of it, and this is a small snapshot. I asked Faisal to give me yesterday, and then we just imported it. I just made a copy of it locally, And then, so this is very similar to the pattern that you have seen with Sensex. Sensex was all numerical data. This one is a data that is like, it's all string data. So I imported the jobs. I'll show you what happens here. So this job has essentially title and company. There are a lot of other fields like, URL to the job description and all that, and we got rid of that. I just took 2 fields, and then I said title and company. So I imported all the jobs, and we have this information, and it automatically formats it and prints it. That is the beginning, and then I was talking to you about tail before. These are the jobs in the end. Which jobs are numbered. So we have about 5,775 jobs. These are all the companies. I copy it into a data frame. That is another interesting thing that you can do. You can do certain functions and then copy into other data frames, and you can manipulate these data frames too. So, and you can keep on creating these structures, and you can play around with them. So once you copy, let me see. Then I print out a bunch of these. Then I noticed there's a bunch of them, and I think there was some mistake I did, and it got a lot of blank lines in between. And later I sorted and removed it. So there is a whole bunch of things which are not a company. It's known, it's a null value equivalent kind of stuff. So I tried to filter that out. So we found, for example, I kept some. So you can filter. So what you can do is you can filter. For example, in this you could have given slightly different strings. You can say company contains this name, then you can find out all the jobs for the company, and you can play around with this a lot. So this is where I kind of stopped. I said, okay, what do you want to do? So in summary, if you really look at it, Pandas gives you the ability to create these data structures, a series which you can generate, or series that you can actually assign from literal values, data frames that you can import from a variety of sources. If you have a source which is different from, I think it's JSON is available, PDF, HTML, CSV, and you can then play around with it. You can name them, and then you can do a wide variety of things. And you can plot them, and which is basically what Faisal's demo is going to be. He's going to show you what are all the different kinds of graphs that you can draw with the data. And I think you're doing mostly with the jobs data, right? Yeah. Everything is from the jobs data, and you can play it. See, it's such a simple library. What is amazing was that hardly must have spent about an hour or so to get this up, and I didn't know anything about pandas before. So I just got up, and in between watching cricket and doing breaks, I just went and typed these kinds of things. And with the IPython notebook, you start building this, and it's really, really cool. So I'll show you just one other thing before I leave, which is not the IPython notebook, but do you have the internet access here? Oops, what happened? Hot Wi-Fi. Oh, okay, clever. First I thought I'll make a presentation. Then I went and saw this. This guy, Wes McKinney, has written a book on data analysis with Python. It's a really good book. He talks about, he does not really talk a lot about, the book doesn't focus a lot on machine learning aspects of it, a little bit, but a lot more about all the stuff that you can do before. And then he covers, a lot of pandas. And I'm not going to run through the whole presentation, but I just want to take you to the, it's got like about, okay, boss. So there is a whole bunch of stuff in there. You can go and see this presentation itself. No, I think this is not the presentation I wanted. I wanted something else. But I just will take you to the last slide of the presentation and show it to you. I think it's, is this the one? 23 slides, yeah. Okay. So to summarize, essentially text file data loading, structured data, Excel, and then they even have a module to read from databases. And I've not tried that, but we'll try it before next session. Plotting we're going to see in a minute. This is the one slide I wanted to show you before I turn it over to. You have group by, which is like what you get in SQL selects. You have a time series data. So if you can actually mark one, it can recognize a date and a time. You can mark one of the columns as a date, as a date time, and then you can do the plotting, and then it will give you all kinds of interesting plots from there. There's a whole bunch of analysis. I don't even understand some of those kinds of things. Rolling correlations, things like that. You can do sampling. So there is a whole bunch of stuff you can do, and the way I look at it is one of the best in-memory database kind of structures that is callable from Python, that's fairly easy to use and hardly takes any time to learn. Okay, with that, Faisal, it's yours. So Faisal will show you some interesting plotting stuff that we did in the same job state.
So I'm not going to show you something complex. It's like all simple things. Okay. So even though I have not even included any multiple hierarchy of pandas and all those things. Pandas has a lot more features to be explained. So initially you load. Okay. So he said that you can load a CSV or any other format. Okay, where there is no titles or names specified. Okay, so normally what happens is that first column is taken when you don't have this names is specified, okay, as a name. So when you specify that, it takes from the first column as a values. So here I just load the same data what he has shown you. Okay, so this is like same data will be loaded into data frame called data now. The variable data has a data frame which has all these jobs, title, and company name. So then what you do is here, you just take title, okay, and say that take a count of title and print top 20. So you take top 20 of titles and make a plot. So what bash bar h is like bar horizontal. So if you just write bar, it will be bar vertical. So it will be like this way, and top like it will not be readable. So just like turned out. So now it's taking top 20. This one title count on the frequency. So actually value count actually gives you the count. It is a you can get a dictionary out of it if you want. So you have to write dot to underscore dict of. That will return you a dictionary of the like whatever value versus count.
Already sorts it.
Yeah, yeah. So it will be giving in the sort. So if you write head, right, actually it will be highest first and then like next. Tail means lowest will be there at the bottom. So same thing where the company names are taken previously in the title. So what exactly here it is doing, if you clearly see the name attribute, whatever names you have specified, it is taking as an attribute here. So data frame has that as an attribute in it. So how exactly it works is that whenever you load anything with names, or if you don't specify the names, first column. So what exactly it does is that, can I have a desktop? Yeah. It's okay. So you know that class has this so this is a dictionary of the object. Okay, so this will have attributes of object. Okay, so the names are loaded into it, so it just adds the names to it. Okay, so it's easy to understand when using it. So this allows you to modify the attributes dynamically in Python. Okay, so that's how pandas work. Okay, pandas takes the names and adds into object. So that helps you to access as if the data frame is called data. So how it actually helps you is like data dot underscore underscore dict. Okay, all these names are loaded. Okay, so you had name title and connect it to the in-memory link. So in-memory table, you say this is a column title. Okay, this is where it has to be pointing. Okay, so whenever you take that title, so you can do data dot title. So this will directly point here, this column. Okay, so this actually, since this is a pandas data frame which understands how exactly it has to be processed in memory, so it takes this pointer and says, okay, this is a offset for this column. So first column has 0 offset plus if it is at the first column, else if it is second column it has certain offset. So then actually row length. So that's how it in memory it points to the right location and gets only those attributes to be manipulated. So when you request for this, it gets only title, not company, nothing else. So you have a list of titles. So you take the list of titles and then you so just yeah, you have list of titles from the data frame and then you do value count. Okay, so you have a column, title column, you do value count. So it counts how many has the same repetition. So you take top 20 with the highest count. So similarly, it's for even another column called company. Since here only 2 columns, I'm just doing it for the both of columns. So if you want, I'll just print what is there in the. So I'll just add. So I just took first 20 and printed it. Okay. So this is how it gives. So you can convert into dictionaries. Now it's not dictionary, it is still pandas object. Okay. So if you want to convert into dictionary, you can use .dict. Okay. But you can't take the first element by specifying 0. Okay. So it's not a list actually. So it's still pandas object. So if you put a 0 here or 1 saying that first or second element you want, it is wrong. So you have to specify value of. So values of you can specify will give all the values, or if you want only one value, you have to specify dot value of and index. So that will give the right indexed value. So in this case you see, so you take this is well understood in pandas. Okay. So how exactly this will be hash mapped? When you write this, actually this will be hash mapped. It says, okay, this column we are having this should be filtered out. Okay. So you say in data frame, okay, the location which has this company, okay, data of company, the column equal to this has to be filtered out. Only those should be taken. In case of numerical data, you can say, okay, greater than this value or less than this value, not equal to this value, but you can't do in. You can't give a list and say in. So you, in that case, what you have to do is that you have to write a multi-index and just go into it. So I am not explaining that in depth. So then, so this again returns you a table which is filtered out only with this. So now you have a pandas table, okay, whatever data set, whatever you have given, with company name only this one. Okay, you have company name all with the same, whereas different titles for that company. So you have filtered out, and then you say, okay, from that I want title names. Okay, and then you say again value from count. Okay, so value count. So you just say, okay, in this company, what is the frequency of titles, and let me plot it for the top 20. So you say, okay, now you see this .NET is the highest one, which is posted from this company, Asus Technologies. Okay, so they take more .NET developers. Out of 52 job posting they did, almost 15 are .NET. Okay, when you see the second one, that is very less, 3. So it's like all others are very less compared to the highest one. So you can say that company is like, when you have like, it's only for like 1 month, not even 1 month. Okay, so if you take years of their job posting, you'll see, okay, so many jobs have been posted by this company. So this company is mainly working on this technology because they recruit highly for this technology. So when you have been expertised in some field, you can say, okay, which company I'm supposed to look. Okay, you collect all different job posting from different places and say, okay, this is the right place. Okay, these are the top 10 companies where I can go and join. Okay, this will be the, so you can then fit, okay, if you want, you can make another criteria, say salaries, and say, okay, filter between these two. Okay, so that also will be easy for you because pandas allows you to do smoothly. So So in this is like in the list you have taken the top job, whatever key. So you saw, right, keys of 0. If you want only the element from the first is like not the count, then you can do keys. So it will give the attribute name means title here. So I'm just printing that. Okay. So here comes like you can even do multi-indexing. If you say that okay, this job posting, in this case it is not, but in some cases it is like this hierarchy. In this case it's not a hierarchy because titles, same title will be from different companies. Okay, but in other case it may be like company pointing title. So in that case your actual table may look like this. So this may be requirement, so this may be company title, so So this may be your structure, for example. Okay, so you say this company has this, so you can clearly build that. So in this case, if you do that, you will have many null values. Okay, so and here not a number. So what is this not a number? First of all, you might have seen the array also showing not a number. Okay, so anything null values it takes as a not a number. So you do any operation on not a number, okay, NaN, it actually returns you not a number. Okay, if you take a not a number column and add it with another any value, okay, it just returns you not a number. Okay, so this is like, this is to avoid the errors that can happen while computing. This is just to avoid the errors that can happen while computing. So anyway, if you are doing something, in all those cases you may filter out saying that, okay, in this case, this is not available, you have to ignore. If this is not available, you have to ignore. So what you can do is you can simply compute, and at end of day you can say, okay, all this not a number has to be eliminated, because there is something which is going wrong. Okay, so that makes your life easy to calculate and all those things.
Just out of curiosity, the .NET developers raw count is how much? You just scroll up.
So total is 62.
You print it without a plot and you'll get the number.
Yeah.
Yeah, you had printed it. Right? So there are total is how much?
Total for this one,
Yeah, .NET. How many jobs are there? 60.
62 or something.
Yeah, 62. And of them, 15 jobs come from that company.
Yeah.
This is based on that small sample.
Yeah, yeah. No, but it does the top, right?
It does the job.
Yeah.
Sample from
61. So out of 61, 15 are from that company.
In fact, all the .NET jobs, if you do it like this hierarchy, there are like developers, architects, and web developers. So that sum is about close to 100, 103.
Yeah. So these are the whole .NET. Still Python comes like.
You remember what was the search we did for these jobs?
Huh?
What was the search we did for these jobs in India? Was it for data science? Or
No.
was it for,
There was
it
like,
just developers.
no, there was like so many different, it's like almost, it's like I took a subset of searches, okay. It's like we have more than 3 million job results. So out of that
So
I
you took
took
about
a,
5,000.
yeah, it's a small subset. Not even 5,000, 2,000 something. It's like, so you had 5,000 because all null values in between. I'll just plot this also. This.
So an interesting problem would be is that
So just
if I
I
have
set
these
up it.
five skills, what are the companies that hire for those 5 skills kind of stuff, right? The probability of being hired by this company, may be an interesting problem to do. And one of the things that we wanted to do, but we'll do it, is that take from the job description, do the skill analysis, and come up with the skill keywords. Right now, we're doing just based on job titles that they give. But when you say .NET developer from one company and .NET developer from another company, need not necessarily mean the same skills.
Can I also make one comment? So for instance, here, you could again have a line-based classification task. So I have a bunch of skills. Tell me the company which I think most go to. So you first learn from this data set that, okay, this company wants these skills. You build up a line-based model. And then you take your set of skills and query the model which is the company that I want.
Yeah. Yeah, that will see. In that case, you know what are the skills you have. It's easy to find in the given job description whether this skill is there or not. Okay.
Yeah.
So
it's a classification task.
Yeah.
So I want to know which is the company which is most likely to hire me.
yeah, that's what I'm saying is like in that case you'll understand, okay, all these skills are needed and all other skills which they need are not there in me. Say what is the percentage of skills they are required, like out of they mentioned, which are mandatory I am having. For example, they said these 5 skills are mandatory. Okay, I am having only 4. Okay, I may have other skills, but you can look into other skills and say, okay, there's like 80% chance because of this, but you have other desired skills which are all matching, so you may get in, more probable.
So here you don't have any training data. So you need a data from the companies, okay, which said that, or at least from something which says that I did this advertisement for this skill set, and I actually hired somebody with this. I actually hired somebody with these bunch of skills. Right? So that's my positive training data. That's my supervised data, right? So the companies hired these people. They advertised for this job, and they hired somebody who had these attributes. So then you can build a naive-based model like that. That, given these attributes, this is the kind of person the company will want. Okay, and then you query that model.
So one more thing that people do in company analysis is they do profile matching. So they have job profiles. They have job profiles and skill profiles, and try to find the match. So you never get people with all the skills that you need, because everybody's list is a big list, and they're all like super programmers that don't exist. So what you try to find out is highest probability of certain skills and the highest skills that you have. So you may have 10 skills, but your Java skill may be far above your JavaScript skill. So you can rank your skills, and that is something that you can try to do. For example, in this company, Future Focus, what we do is we send out a bunch of resumes to anybody who wants to recruit, and then they select only a few people. So from this, we can look at the profiles and say who are most likely to be recruited, and send only those profiles, for example. So that way, you don't send out too many useless profiles to the customer, so you can improve the customer quality kind of stuff. And so we are interested in the job analysis of data. But we also want to see in a certain region, like in Chennai, what are the most demanded skills. So these jobs also have the location of the company's location. So we could do a much more, this we're just demonstrating pandas, right? But you can actually, when you take it up as a job, you can say, in different regions of the country, what are the most skills in demand? And depending on if you have the skills X, and then you can move to this portion, or you make more likely to get a job in Bangalore than in Chennai. Those kinds of interesting ones you can do, model different.
Yeah, and I think maybe you had asked the question about weightage, right? Yeah. So here is another instance where you actually, I was talking about those utilities, right? So here you can actually, instead of weightage, you actually give utilities. So if I want the Java programmer, that you must have Java skills, okay? So if you don't have Java skills, I'll immediately reject you, right? So you can have a whole bunch of utilities like this, or Java skills, this skill, that skill, blah, blah, blah. And then you try to maximize the utility, Okay, so you do the matches and then maximize the utility, and whoever has the most utility is the candidate, or you rank by utility.
So in case of like Java skills or something, they will be asking what exactly in Java. Okay, so they will mention what exactly it is within that. You may say, okay, I know Java basic. Okay, so you may be taking that, right? But exactly it will be there. There will be hierarchy in Java. This one is needed. So if you don't have that in Java, you are not eligible, right? That's how it should be. So when you apply for it, you may say, okay, I have Java skill, so I may apply. So even some referrer, document referrer or like job referrer says, okay, you have Java skills. This document says it needs Java skill. So it may show it, but that is wrong. It should not be shown, right? If you don't have a specific skill which they are looking within Java. Java is a technology, it is not a skill. Okay, so skill is something else within it. So you may need to be knowing some J to E or something like. Okay, so this is like no filtering is done. Okay, so in case if some filters has to be done, then first of all jobs and all would have gone because stop words. Secondly, it is unigrams, no bigrams is done. If at all it was a bigram, then or trigram, then it would be like senior .NET developer would have been the highest. Okay, so that is like, so it's like simple word splitting I just done. So you can just change it to n-gram models. You can see the best n-gram frequencies and say, okay, these are the top to be sent. So you say developers are occurring 5 times, okay, and senior .NET developer is happening like 4 times. Still you say that should be senior .NET developer rather than just developer. So that's how you find which is should be the n-gram. You don't say one or like is like this is like more than 50% chance, then longer string has to be considered rather than shorter string. That's how n-gram has to be built in. Okay. Yeah. So this is like just printing like top 10 company names which are having like highest this one. So in that period of time, Asus Technology has put up like 52 requirements. You saw that. Yeah. So you saw that 15 were that .NET requirements. So if you do an analysis on percentage of requirements in this month, this company is doing, you may see some other company is actually standing better for some other title. So you may have to, instead of looking into this company, if you have Java or something, you may have to look into some other thing. So I'll show you. I hope.
We need to modify data bit, right, to do some kind of analysis. Like, suppose associate software engineer in one company might be software engineer in so, but if you do just having a table of strings, so
That's basically what all these compensation consultants do. What they do is, they normalize your jobs based on the pays, and then they'll say associate engineer in Wipro may be equivalent to senior engineer in some startup or something. So they do all this. It's actually very complex.
Yeah.
Complex. Here, what you can do is basically skills, demand for skills. You can find out regions, companies, skills, what they look at. The skills have to be n-grams. They can't be like single words or milligrams.
because in product companies they could be calling us something else, software engineer or some like data
software engineer, software developer,
yeah.
software specialist. They all have like equivalent names kind of thing.
Like similarly data analyst is synonymous with data.
So what you need is a kind of a taxonomy or a hierarchy.
Yeah.
When you say Java skills, you can say Java front-end skills back at a very high level. You can say front-end skills, back-end skills. Which is front-end skills, you are probably more like an Android developer or applet developer. Which is back-end skills is mostly more like Tomcat or that kind. So you start think,
So basically, again, we need to group it.
So clustering will come into the picture there, right? So you want to actually, deeper level clustering and classification to some extent. You want to put these groups of skills and when you become very specialized. So I want Hadoop developer, most likely to be Java developer. And if you're going to do Hadoop, even though it can be done from different languages, then you can find out what these things are. So you need to start further grouping. This is very simple, like a flat table kind of stuff.
Yeah, but you could also just again think of it as a network now where the attributes are now not independent, but they're actually now dependent attributes.
So he was speaking about smoothing, right? So actually NLTK has smoothing, but some mathematical error we have to sit and solve it. Okay, so we'll be doing afterwards. Yeah. So it's like a lot of bugs where everyone is blabbering. It's like it has to be fixed. So, okay. So here's simple example how smoothing can be used. Okay. So here's like Laplace probability distribution smoothing is used for estimator. So you take n-gram model, how exactly it has to be, how big the n-gram should be. So in this case, it's like you're saying, okay, maximum 14 character n-grams.
Okay, never mind.
You stand there.
So I know it. So I don't want to invest. It's like, okay, this is like, I'm here just I'm plotting that how randomly text can be generated from the. So as you were trying, Karthik, so you were trying to generate text, right, from a given text. So here also it learns from the n-gram model. So it has a model and it uses the Laplace distribution and predicts what should be the text. And it says probably this would be like multi-word statement or something like that. Okay, so.
Maybe you should say what the corpus is.
Yeah.
Everyone knows what the corpus is.
So corpus is indus corpus. Okay, we are using. So Harappi scripts. Okay, so I'll show. I don't need. Do I need to show that?
What is
So corpus is nothing but a bunch of tagged words which forms a sentence. Okay, so in NLTK you can specify your own corpus. So you can put your own corpus and ask them to pull.
Actually, corpus is basically a collection of
Collection of words which is tagged to a specific sentence unit. So it may be verbs, vocabularies, or something like that.
Yeah, so what Faisal is doing here is building this n-gram model, right? So it's n-gram is basically a language model where you have conditional probabilities. So the probability of a word is just factorized into conditional probabilities. Or so if you take the probability of a sentence, for instance, the probability of the sentence is the probability of the first word in the sentence times the probability of the second word given the first word, probability of the third word given the second word, etc. Like that. Okay, and depending on how many words you condition on, that is called the n-gram. Like if you just condition on pairs of words, then it's bigram. If you condition on 3 words, it's trigram, and so on and so forth.
In this case, it conditions on 13 words, so it's like 14 gram.
No, it doesn't condition on 13 words. It's still conditions on 2 words, but the
it's,
length is.
In this case, it's 14.
Oh, you condition on 14.
Yeah.
Okay, but you won't have much data for.
Yeah.
I mean, the language model will be very poor.
Yeah,
Okay.
this is like so. I have like other one by.
Okay. So then so it doesn't matter. So the n-gram model can be built with anything. You know, it can be built with letters, words, symbols, musical notes, anything. So it doesn't matter. What the object is doesn't matter. So what Fazil is doing here is building an n-gram model for this Indus script, which is these symbols. Okay, so if you've studied, if you remember your high school history, the Indus script was written on these seals, and those are the sequence of symbols. So what he does is so we have the corpus. The corpus is just a collection. Each line of the corpus contains one sort of seal, writing from one seal. So it's a bunch of symbols like that. So you go through the corpus, you estimate the bigram, trigram, etc. frequencies, you do all your smoothing, and then you generate a language model. And then you can use the language model to generate new text. It's like, I think, two lectures back we spoke of this dissociated spreads algorithm, right? Where you take the Bible and you learn n-gram models from the Bible, and then you try to generate data which seems like it's kind of biblical.
And you
so
may
it's a
see
similar
like
idea
more
here.
than one probability,
Yeah.
which is mistake of that. And
yeah, so it gives you random. So that's where the bug is. It gives you probabilities of more than one. And Karthik has also done this for Tamil.
Uh-huh.
Yeah.
It's 2.8 at the bottom.
But there's also e power minus 7. Okay. But there are situations where it's giving.
no, somewhere.
Yeah,
else
it gives you more than one
yeah,
probabilities as well.
Not in this case.
Yeah.
Somewhere else. Yeah, somewhere. I don't know whether in this case or.
Yeah, so you can, what is the application? So the application is basically to try to understand so you can't decipher this, or at least it has not been deciphered yet after a lot of effort. So one of the applications is even if you cannot decipher it, can you understand if there's any syntactic structure in it? Okay, so just try to understand the syntax of the script, like the mechanics of it, even if you cannot understand meaning. Okay, so one way to understand or try to impute syntax is through these kinds of models, n-gram models, and
There is when I was looking at this, I suddenly thought of the other one. So there is a problem that we are struggling with to try find out key skill. So key skill cannot be, we do brute force like unigrams, bigrams, trigrams, and kept on going there. If you look at cloud computing, it's 2 words. It's a bigram, right? If you look at software as a service, it's like 4 words. So when you look at a stream of text, you don't know which ones are the ones that actually follow, right? So what is the probability of software as a service occurring in something like that? So when you go and start building an n-gram model where you say when software occurs, the chances are that there is software followed by developer. How many occurrences of software developer or developer of software, those kinds of things occur. So you can start coming with all these probabilities. So from raw text, you can try to extract skills, and you can use probability modeling to some extent for doing this kind of thing. So that's
Just to continue on that comment. So for instance, if you look at the probability of software as a service, this phrase, the simplest way to compute this probability is to say it's the probability of software times the probability of as times the probability of A times the probability of service. Okay, this is your naive estimate for what the probability should be. But then you will see in the text, the probability is actually much higher than this, because software as a service is coming together. It's not just, you're not just choosing them randomly. So the moment you see the probability of, say, an n-gram is much higher than what would be predicted by, say, a lower order model, like a unigram model. So this multiplying all the probabilities is the probability of a unigram model. If it's much higher, that means that object is actually occurring together. And that gives you a signature that this object must be what is called a collocation. So this thing, words coming together are called collocations. So this is like a simple way of finding out collocations. So that's another utility of this kind of model. Yeah, so again, with all of these things, there are always measures of, so if the probability is maybe only 1.2 times the probability that you would get from the unigram model, is that a collocation or is not a collocation? Or if the probability is 10 times more, then of course maybe it's a collocation. Okay, so with all of these probabilistic estimates, there is always uncertainty about the level at which you will decide something, and that can only be decided by the utilities.
There is also context. So if the context is cloud computing, so if there is an article on cloud computing, the probabilities of these things occurring is much higher than if it is some random, like, some business text, for example. So there is context is something that we need to start putting into the model too, because that starts giving you a little bit more information. So.
So this is one bigram model. Okay, so what he said.
So maybe explain just. Will you explain what the Witten-Bell smoother is, or shall I explain?
Yeah.
Okay, so we were talking about these smoothers, right? So the smoother that he showed last time is essentially one of the Laplace smoothers. So where you just take the count, add to the numerator, and add to the denominator. This is a bit more fancy way of smoothing. Okay, this is called the Witten-Bell smoother. So there are whole families of smoothers. This is a bit more fancy, and it makes stronger assumptions about. So there it makes no. So what the Witten-Bell smoother does is it also. So if you're trying to estimate the probability of an n-gram, it uses information of the probabilities that you've already estimated of the n-1, n-2, all the way up to 1 grams. Okay, so if you're trying to estimate a bigram probability, it will use not only the bigram counts, but also the unigram counts. If you're estimating a trigram probability, it will use the bigram counts and the unigram counts. Okay, so it's a bit more sophisticated way of estimating the probabilities, which is a little better than just the Laplace kind of add one smoothing that we were talking about. So NLTK has all these smoothers built in, which is very nice. Okay, they don't work, but
Yeah.
we have committed to fix the smoothers. Yeah.
So they have a lot of smoothers, but
Yeah. Not all of them are guaranteed to work. Yeah, so there you can see, oh, that's the entropy. Okay, but there are places where the probability is coming out to be more than 1. So, yeah, no, that's just the entropy. Yeah.
in this case also it gives more than 1 actually.
Ah, okay.
For 14 words it doesn't come, but
I see.
bigrams it actually gives.
Yeah. So the point here is what? So you can see So what is? Can you explain what's going on?
So this is a given sample, okay, random sample given, okay, and it generated this as a text. Probably this should be the text or the string. So it says, okay, so you say 6-character string out of this starting.
So you say I want a 6-character string in which that particular combination occurs.
Yeah, that is a starting part.
Oh, that is a starting point. Okay,
So
right,
it just
right. Yeah. So in English, this should be a So for a n-gram application, I start the sentence with the first 2 words, and then you ask the model to complete the rest of the sentence. Yes, exactly. That's exactly the same thing here. So you type the first word, and it automatically gives you a couple of next things for the searches, right? So it's exactly that algorithm.
Yeah. So you may type the first word or n words. So it says what next n words.
What is a
should
probable next word that you might want to type?
be. So
We call it intelligence. Intelligence. Yeah. Okay. It's also like the T9 in the phone, where you are sort of predictive text.
Google Suggest has that.
Yeah. Google Suggest. Yeah.
This is more the dot net things which gives you the syntax completion times. So, but they are done slightly different. Google has the entire n-grams database available to you.
Yeah. Yeah.
Special database structure. They moved away in 2006 from databases because it's slow.
Yeah.
So they go for indexing based on image counts.
Hmm.
So the special architecture customized. No page ranking. Page ranking. Yeah. Page count. Ranking is different as how it is.
Hmm.
So NLTK allows you to build your own corpus and use it this way. Okay, so you can build your own corpus and import your own corpus with your own name. Okay, so we have the used as name as index and just like importing that. Same thing you used to do with files, and you have set of operations defined. So you eliminate that, you put all those operations which are 90% chances to be done, you just put, or like if you are have more time, you can put most all functionalities and just make the corpus so that it is easy for you to function. So what we are thinking of is like incorporate pandas to this index so that you will have all the functionality and you can easily work on it. Okay.
So just to again explain why pandas is necessary, these seals actually come from a archaeological record. Okay, so there are a bunch of seals which come from Mohenjo-daro, bunch of seals which come from Harappa, bunch of seals which come from, so in addition to the symbol, there's also another column which says where it came from. There's a column which says which
side it is written, which direction it is
so
written.
what kind of artifact is it written on? Is it a seal? Is it something else? There are a whole bunch of different kinds of archaeological
what symbol
artifacts.
occurs with it.
There's another, what symbol occurs with it. Another information is which archaeological level was it found in. So is it like a very old record or is it a very sort of newer record? Because as you dig deep, sorry? There are also images. Yeah, so these are actually seals. They're actually real objects. Yeah, so they're real objects in which the thing is inscribed. So it's like a clay tablet.
So, but what we take as an
Image.
Is an image, yeah.
but again the same problem of which angle it was taken.
So there is actually a concordance. There's actually a book from where all of this is coming. So Faisal, if you just keep talking, I'll get the book and I'll explain.
So till he get the book. Okay. So here what you can do is like, even if you don't have like plotters which can do whatever plotting for yourself, okay, because all these plots, whatever inbuilt, you can't do many things in it. So you can use some other like D3 and all, like, and customize it to have some extra features. So in this case, I wanted to put the image on the top of it, whatever the character. Okay, so in this case, it's just doing frequency, but in other case, it can. Yeah. So it just says. Okay. So in this case, it just says frequency because unigram. Okay, but in bigram and trigram, I just made for the entropy and probability calculation, where it brings out a matrix and pseudo color plot. So it actually says like it's not loaded properly because browser is just hanging.
More than bigram, I can't plot, right?
No, you can plot this even in bigram, but here it's not loaded, I think. Yeah, it's not loaded properly. Else all the icons come here and it's like when you hover, it just shows what is the probability between this occurring with this, okay? So it just shows entropy or probability. In this case, it's entropy.
Okay, so maybe if you can just give me 1 minute. So this is the book which has all the. So this is the book. It's called the English script, concordance, text concordance and tables. Okay, what it has, if you look at it, this is a book. One of the earliest instances of actually compressed data analysis. Yeah, this book is from 1970s. It was done by somebody who is living in this city right now. His name is Hayat Mahal. So what it has is just stuff like this. So there's a number, a bunch of numbers, and then this is the symbols, bunch of symbols. So it goes pages and pages of this stuff. So the entire corpus of the interscript, so whatever was in it. So what Faisal has done is taken this data set. Thankfully, this is available electronically. You don't have to actually go and sort of manually type all of this. It's actually available electronically. So he's taken this thing and he has put it into the. So now instead of doing all of this analysis by hand, which was actually done manually before full computerization came about, what we're trying to do is there's a lot of information here. All of the information has not been extracted. So what we're trying to do is take it, put it on the computer, and then try to automate all of this thing and see if we can get some new insights. Okay, it's an old problem, but I think putting in all this computer technology, machine learning and stuff like that, I think we can get some new information. Okay, so this is just for fun, but I think just by having fun you can learn a lot of things. Yeah. Oh yeah. Okay, so let me tell you why this project. Okay, and what is the context. So the thing is that this is in the script. It's called the script. Okay, but you know, if you again remember the history, Indus civilization was discovered around the 1920s. So this is almost 2020, and it's 100 years, and still nobody has been able to decipher this. Okay, so there's a big unsolved problem here. And now the issue is that about 5 or 6, 10, maybe 10 years back, there's a sort of theory from the US, 3 archaeologists, one Sanskrit person, one historian, and another sort of linguist guy, who said that, look, there's no point trying to decipher it because it's not even a script. Okay, it's just scribbles. Okay, scribbles of, so they were not very precise as to what the alternative is, but they said that it's not a script. Okay, it's not, this does not represent the written, the spoken word. So it's not a direct, so from here, there's actually nothing linguistic encoded. Okay, so the question we were trying to ask ourselves was, so the only way you can refute that is to actually give an explanation. If you can decipher it, then yeah, and then everybody accepts your decipherment, then you can clearly say that yes, it is linguistic. But if you do not decipher it, how do you decide whether it's linguistic or non-linguistic? Okay, so I have a classification task in my hand. I have a script, right? It's a bunch of sequences. I want to know, is this a bunch of sequences which is a linguistic sequence, or is it a bunch of sequences which is a non-linguistic sequence? Okay, and now the point is that what kind of sequences are non-linguistic sequences? If you have the DNA code has a lot of AGTCs in it, right? Now that's a sequence. Now that has information because those AGTCs are coding for the protein, right? But it's not a linguistic sequence. It's not coming from language. Okay. Similarly, if you have music, you know, sare gama, blah blah blah, that's also, you know, coding information, but it's not linguistic. Okay. So you can have sequences in which there is structure, but that is not linguistic structure. So the task we had set ourselves was, given this sequence, given the fact that it still has some structure, is it possible to distinguish whether this structure is coming from a linguistic bunch of things or a non-linguistic bunch of things? Okay. So we set up a naive Bayes model, and the naive Bayes model had only one attribute. Well, it had 2 attributes. So Faisal, can I take 2 minutes of your time? So it just had 2 attributes. So the attributes we chose was essentially this thing called the entropy. Okay. So this is my sequence. So very, very simple. It's absolutely dead simple model. So the sequence can be either linguistic or non-linguistic. Non-linguistic. And the entropy can have a value which is continuous. Okay, and now what the first thing that we did was we looked at a bunch of, so again, the question of training data and test data. So we went and looked at a whole bunch of sequences which we knew beforehand were linguistic, and a whole bunch of sequences which we knew beforehand were non-linguistic. Okay, so no, because Indus script is supposed to be test data. Okay, so we don't look at the Indus script right now. We just look at a bunch of known linguistic scripts and a bunch of known non-linguistic sequences. So here we looked at Sanskrit, English, Tamil, various bunches of things. And here we looked at DNA sequences, protein sequences, music, and Fortran programs. Okay, so Fortran programs are also sequences and very structured, but they're not linguistic sequences. Okay, and what we found was this, that if you plot the entropy as a function of the number of tokens, then for every linguistic sequence, this entropy has a certain value. Okay, and for non-linguistic sequences, this entropy is either very low or very high. Now, this entropy is a measure of the amount of constraint that you have in choosing the next symbol, given that you have chosen the first symbol. Okay, so for Fortran code, the entropy was very low, right? Because in a code, once you've chosen the first, once you've opened a brace, in a C code, for instance, once you've opened a brace, you can only put a finite number of things after the brace, right? Or if you opened a square bracket, you can only put a finite number of things after the square bracket. So once you've chosen one symbol, the next symbol that you choose has very little freedom. Okay, so this gives you a very low value of the entropy. Whereas for non-linguistic sequences like music, once you've chosen a note, you have a lot of freedom in the next node. You're constrained by the raga that you're operating in, but you still have a lot of freedom in the next node. If you have a protein sequence, a DNA sequence, there's still a lot of freedom. Okay, so then the entropy values are high. Language, it turns out, is to be an intermediate value. Okay, so now once you have this, your model is trained, then you compute the value of the entropy of the index script, and then ask the model, given that the entropy is this much, tell me whether is it a linguistic category or a non-linguistic category. Okay, and using this type-based classifier, what we found out was it's actually linguistic. Yeah. Yeah, of course. The entropies be bounded, right? So if all the probabilities are, so I have, so the, if I have n tokens, right? N tokens, then the probability simplest, naivest assumption of allocation of probability is 1 by n. All the all the things are equiprobable. Okay.
The question is for linguistic. That above the linguistic line there is something which is non-linguistic, and below that there is something
Linguistic. Yeah, exactly.
There should be a bound.
There are bounds. Yeah. So the bound is the maximum entropy that you can have is when everything is completely uncertain. All your symbols are equally likely, and then the probability is 1 by n. So p log p, 1 by n log 1 by n. That's the upper bound. And the lower bound is when all the symbols, maybe there's only one symbol. Only one symbol can occur. So the probability is concentrated exactly in one thing. And then the entropy is 0. Right? So the lower bound of the entropy is 0. The upper bound of the entropy is determined by the size of the corpus. Okay, and that's why you can see that this is closed, small, and this is. So there are min-max bounds here. Okay, so that is why Faisal is trying to compute the entropy. So the entropy is now an attribute that you use for the classification task.
So you may see this almost the curve which is looking similar to the intermediate whatever he has drawn.
Just one attribute. Yeah, it's a one attribute. So that's why people got very excited about it. That why are you using only one attribute? So a lot of the controversy that was there. So this work, if you go and do a Google search for this, you'll see it generated a lot of controversy. So 2009, I became briefly famous because of this work. so there's a lot of controversy generated because of this work. And one of the reasons was, there were two reasons. So first of all, people didn't understand that we were doing Bayesian classification. Okay, so they thought that this is proof. It's not proof. So whenever you're using a probabilistic model, you never get proof. You just increase your likelihood or you decrease your likelihood. Okay, so in this model, the criticism of the model is that yes, it is only using one attribute. Okay, but so you can increase the number of attributes. So this was just the way I look at it is this was taking a machine learning algorithm and applying it to a problem of history. Now that hadn't been done before. And now you can try to systematically improve the kind of things that you can do. You can put in more attributes. You can decide those attributes, how those attributes are linked. So there's a lot of work you can do to improve the problem or the way the analysis is done. But okay, so Faisal is trying to do some of those.
Add more data, show more data that it's true, whatever you had.
So yeah, so for instance, you can increase the number of things that you take in the training set. You can take many more languages. Okay, so and many more here. So you can get more confidence on the model. So all of those things can be done. Is that color difference?
No, that is just like higher the entropy, it's like bad. Yeah, this is like.
Yeah.
So higher the entropy, it's like reddish.
So you could do this for English.
So you just plot this. Here I just made a bar graph, but you can plot it as a line graph which will be curve. So you can just plot for various languages and see which curves are actually in the same bound. Okay, so you find that okay, all of these are linguistic, which falls in the same set, and others just go below or high. So you just like eliminate those. And if whatever your training set is Indus or some other language which you are trying to identify, if it is falling in the same where linguistic patterns are there, then you say, okay, this also should be linguistic. That's how it is. So it can be done even for like multi-grams or something like that. Here it's like for just.
So this is the skeleton of the method. You can put more flesh to it depending on how much energy and enthusiasm you have.
So, yeah. So what makes it will not
Yes.
give us a word.
Yeah,
That's
yeah.
the
So
problem.
you don't know what word bound. First of all, you don't know what that token stands for. Is it like a phoneme? Is it like ABCD? Or is it like a full word? Or is it maybe even more than a word? It's a phrase. Right? Because you know how those ancient languages work. You know, the developed linguistic understanding that we have now of taking a atomic sound and representing as one symbol. That understanding had not been arrived at earlier, right? So then, much more crude methods were used to represent sound, spoken word. And so you really don't know what these things are. But for instance, if you just go through this data, you see that these two are very close in frequency, right? You will see that if you go to the record, these two are actually collocations. They almost always occur together. Okay? So you'll see, and once you go through the record, you'll see there are all sorts of these interesting patterns. This is very interesting because this is very low entropy. Why does it have low entropy? You can almost with certainty say that this is the last character. Okay? So this is like the full stop or the end character or whatever or something like that. Very high, with very high probability. And the higher the probability of something happening, the lower will be its entropy. The more certain you are, the smaller is the entropy. So that's why it's got very low entropy. Okay? So you can go through the script just by doing this kind of analysis. You can see lots of interesting features coming out of this, and then that gives you maybe somebody who's more professional at doing decipherment. It can help them.
So actually, I can't load that color plot. Else I would have shown how it is. Okay. So if you would have seen, it's like I don't know, it is loaded or not. I don't think it is loaded.
Another 5 minutes and we should
Okay.
wrap up. Otherwise, no one's going to get any food.
So it's not loading. So anyway, leave it. So in that you can actually see that there are some lines which says that okay, if this word word is most probably happening after this, all those things. You'll see so many lines. Okay, so those lines will give you a clear understanding that okay, this is the pattern how it actually flows. So if you actually do that color plot, you'll make understanding that okay, this is how it has to sequentially flow, because here the entropies are less and probability is high. So the higher the probability and entropy will be low. So you say okay, this is where I can decide okay, what is the next word, what can be the sequence continuous to it. So all these kind of things you can actually make and say okay, this is a search or whatever you are doing, and what is the probability next word should be this, and why I have to pick this, why not the other one. What if one element is missing? So you have a CL or you have a text where one word, intermediate word is missing, and you have two words either side. So you can still decide what should be the best fit for the intermediate. You see that the sum of the product of entropy should be like lower when you consider that. It's like lower the entropy, product of entropy, when you take that, it should be less. So you may say, okay, after this is more probable, but when this comes next, some other words should be fitting here. Okay, so it's like fill in the blanks kind of thing.
Yeah, fill in the blanks or spell check. Like when you do a misspelling, right? It suggests that